Welcome to the Deep Sleep Science Channel. Tonight, we're drifting gently toward the Andromeda Galaxy, a vast spiral of stars so distant that its light has been traveling for millions of years, yet so close in cosmic terms that it quietly watches our Milky Way from across the local group. Before you relax too deeply, you're softly invited to like, subscribe, or leave a small comment if you enjoy these calm journeys through science. Now settle in, slow your breathing, and let's begin exploring Andromeda, its structure, its stories, and the quiet, measurable wonders hidden inside its faint keen glow. Andromeda is a large spiral galaxy in the local group, and astronomers commonly catalogue it as Messier 31, or M31, and also as a NGC 224. These names come from different observing traditions and catalogues, and together they help scientists be sure they're always talking about the exact same object. When you see M31, you're seeing a shorthand that connects modern research papers, telescope archives, and star charts to a single nearby galaxy. It's a quiet reminder that the sky is shared and that many generations of observers have returned to the same target, learning more each time. Andromeda appears in Earth's sky in the constellation Andromeda, which is where its familiar name comes from. Constellations are patterns we draw on the sky, but the galaxy itself is far beyond the stars that outline the pattern. The name is less about where Andromeda belongs in space, and more about where it happens to appear from our viewpoint on Earth. That simple naming link makes it easier for people to find, talk about, and return to it again and again. From a dark site, Andromeda can be seen with the naked eye as a faint, elongated smudge of light. What you're seeing is not a single star, but the blended glow of an immense system of stars so far away that your eyes gather it as a soft patch. The shape looks stretched because you're seeing the galaxy's disk at an angle. Even though it's gentle and subtle, that faint glow is direct evidence that the universe is filled with huge structures well beyond our own home galaxy. Andromeda is one of the few galaxies outside the Milky Way that looks extended to the unaided eye under good conditions, rather than appearing as a point. That extended look happens because its light is spread across a noticeable area of the sky. Most galaxies are too far away to show their size without optical aid, but Andromeda is close enough that its true scale leaves a visual footprint. This is one reason it has been a favorite object for observers across centuries. The distance to Andromeda is often given as roughly 2.5 million light-years, which is about 765 kiloparsecs. A light year is a measure of distance, not time, and it tells you how far light can travel in a year, moving at its constant speed. So when you look at Andromeda, you're receiving light that began its journey long before modern human history. That distance is large, but it's also small compared with the distances to many other galaxies, which is why Andromeda is such a powerful reference point for astronomy. The galaxy is close enough that astronomers can resolve individual stars in many of its regions using large telescopes. Resolve here means the telescope can separate stars into distinct points rather than blending them into a single haze. This matters because once individual stars can be measured, astronomers can learn their brightness, colors, and distribution more directly. With Andromeda, that ability helps connect the broad look of a galaxy to the real lives of stars inside it. Because of its distance and brightness, Andromeda is a cornerstone object for testing methods that measure distances beyond the Milky Way. Distance in astronomy is often built from rungs on a ladder, where nearby measurements help calibrate farther ones. Andromeda sits at an important step, far enough to be truly external, but near enough to study in detail. When those methods agree on Andromeda, it strengthens confidence that they can be applied reliably to much more distant galaxies. Andromeda's total stellar content is sometimes estimated at around 1 trillion stars, though that kind of number depends on models and assumptions. Counting stars individually is not possible across the full galaxy, the way we might count trees in a small forest. Instead, astronomers estimate star numbers by measuring total light, mapping stellar populations, and using models of how many stars of different types contribute. The result is an awe-filled scale, a galaxy that may contain vastly more stars than most people ever imagine, gathered into one organized, rotating system. Andromeda is frequently used as a template spiral in scientific studies because it is both nearby and large on the sky. A template object is one that becomes a reference example for learning how a broader class of things behaves. Since spiral galaxies are common in the universe, having a nearby spiral that can be studied in many ways is extremely valuable. Andromeda helps scientists test ideas about spiral structure, galaxy components, and stellar populations in a way that can be compared to other galaxies. The realization that Andromeda is an external galaxy helped establish that the universe contains many galaxies beyond the Milky Way. For a long time, objects like Andromeda were grouped under the word nebula because their true nature wasn't yet clear. Understanding it as a separate galaxy expanded the size of the known universe dramatically. It shifted astronomy from studying one grand stellar system to studying a cosmos filled with countless galaxies. High-resolution space-based imaging revealed that Andromeda's nucleus appears double in brightness peaks, rather than being a single, perfectly centered glow. This is striking because many people expect a galaxy's center to look simple and symmetrical. Instead, Andromeda shows a more complex arrangement of stars near the core. The double appearance hints that the central region has an intricate gravitational structure shaped by the orbits of stars and the pull of the massive object at the center. The central supermassive black hole in Andromeda is commonly referred to as N31*. A supermassive black hole is not something you see directly in ordinary light. It is inferred from how it influences nearby matter and stars. The special name helps distinguish this black hole from others and ties it clearly to its host galaxy. Even when it is quiet, its presence organizes the motion of the innermost stars. M31* is considered a low-luminosity active galactic nucleus, meaning it is relatively quiet compared with bright quasars. Some galactic centers shine intensely because gas falls inward and heats up, releasing huge amounts of energy. In Andromeda, that activity is much calmer, so the nucleus is not blazing across the cosmos like a quasar. This quieter state is still scientifically important because it helps astronomers understand what most supermassive black holes are like when they are not feeding Kashi rapidly. A famous historical transient in Andromeda is S Andromedae, also called SN 1885 AE, a supernova observed near the galaxy's center in 1885. A supernova is a rare, powerful stellar explosion, and seeing one in another galaxy was a remarkable event for its time. This particular explosion is remembered because it occurred in a nearby, well-studied galaxy and left evidence that can be examined long after the initial bright flash. It connects the calm appearance of Andromeda to the reality that dramatic stellar endings also happen within it. The giant stellar stream is a prominent example of tidal debris in Andromeda's halo. A stellar stream is a long, faint trail of stars that once belonged to a smaller system, like a dwarf galaxy or a cluster, that was pulled apart by gravity. Over time, those stars stretch out along the orbit, forming a ribbon-like structure. Seeing such a stream is like seeing a long-lasting footprint of a past interaction, preserved in the shape of the stars themselves. The giant stellar stream can be traced to very large projected distances from Andromeda's center, showing a large-scale accretion event. Accretion here means growth by collecting and absorbing smaller neighbors over time. The fact that the stream extends so far makes it clear that the event was not a small disturbance, but something that scattered stars across a wide region. This kind of structure helps astronomers read Andromeda's history as a record of encounters and gradual assembly. Mayal II, also called G1, is often cited as one of the most massive and luminous globular clusters in the local group. Globular clusters are tightly bound spheres of many old stars, and the most massive ones can be extraordinary in scale and brightness. G1 stands out because it is unusually substantial compared with many clusters in our own galaxy. Studying objects like this helps scientists understand how star clusters form, evolve, and sometimes blur the boundary between clusters and small galaxies. Some recent work finds roughly coin flip odds over very long timescales, up to around 10 billion years, when uncertainties and third body effects are included in estimates of a Milky Way-Andromeda merger. This is a gentle reminder that astronomy often deals in probabilities when the system is complex. The future depends not only on the Milky Way and Andromeda, but also on the gravitational influence of other large neighbors in the local group. Even with excellent data, small uncertainties in motion today can grow into very different outcomes over billions of years. Andromeda is moving toward the Milky Way with a negative radial velocity, which means it is blue shifted in the Sun's frame. Blue shift happens when light waves are slightly compressed because the source is moving closer along our line of sight. It's a subtle effect, measured with careful spectroscopy, but it carries big meaning. Andromeda and the Milky Way are part of the same gravitational neighborhood. Their motion is not random, drifting through space, but a dance shaped by gravity on an enormous scale. The approach speed is often cited as roughly 110 kilometers per second in popular summaries. That sounds fast on human scales, but space is so vast that even this speed takes immense time to close intergalactic distances. The number gives a concrete sense of how astronomers turn tiny shifts in light into a map of motion. It also shows how precise measurement can make the quiet sky feel more physical and dynamic. In galaxy classification terms, Andromeda is commonly described as a spiral galaxy with a significant bulge. Spiral galaxies have disks with organized rotation, often showing spiral structure, while the bulge is a dense central concentration of stars. A significant bulge means the middle region is prominent compared with some other spirals. This overall shape helps place Andromeda into the broader family of galaxy types used to compare structure and evolution. The bulge of Andromeda is prominent compared with many smaller spiral galaxies. That prominence affects how the galaxy looks and how its mass is distributed. A larger bulge can indicate a complex history, including early star formation and possible past interactions that helped grow the central region. In images, the bulge gives Andromeda its bright core, contrasting with the fainter spread of the outer disk. Astronomers often separate Andromeda into components such as the nucleus, bulge, disk, and halo. This is a practical way to describe a galaxy, because each component has different kinds of stars, different motions, and different histories. The nucleus refers to the very central region. The bulge is the thick central concentration. The disk is the rotating flat system, and the halo is the extended car, outer region. Thinking in components helps scientists connect what they see to how the galaxy formed and evolved. The disk and bulge are embedded in a much larger halo of stars and dark matter. The bright parts you see in photos are only the central, most luminous regions. Beyond them, The halo spreads outward with stars that are far more diffuse and with dark matter that does not emit light but dominates the galaxy's gravitational pull. This surrounding structure is a key part of why galaxies rotate and hold together the way they do. The halo extends far beyond the bright disk, where star densities become extremely low. In those outskirts, stars are so sparse that the region can look almost empty compared with the galaxy's glowing center. Yet those faint stars still matter because they trace the galaxy's growth through time. The outer halo is often where remnants of past mergers and accreted material are easiest to detect. The outer disk of Andromeda is known to be warped relative to the inner disk in multiple wavelength studies. A warp means the disk is not perfectly flat. It bends and twists at larger radii. This is common among spiral galaxies and can happen when gravity from companions or misaligned in failing material tugs on the outer parts. The warp is a subtle sign that even a seemingly calm galaxy has been shaped by interactions. The shape and warp of the outer disk provide clues about past gravitational interactions. Gravity is the quiet sculptor of galaxies, and its effects accumulate slowly. If a smaller galaxy passes nearby or is absorbed, it can bend the disk and leave long-lasting distortions. By measuring how the warp behaves, astronomers can test scenarios for what might have influenced Andromeda over time. Andromeda's disk contains spiral structure that can be traced in optical images and in star formation traces. Spiral structure is not just a visual pattern. It reflects how stars and gas are organized and how the disk rotates. In visible light, you may see the distribution of stars, while in other bands you can highlight regions where new stars are forming. Using multiple traces helps reveal the full structure that the eye alone might miss. The disk contains both gas and dust as well as stars. Stars are the most obvious contributors to a galaxy's light, but gas and dust are essential because they are the raw materials for future star formation. Gas can be cold or warm and can move through the disk in complex patterns. Dust, made of tiny solid grains, affects how light travels and also helps cool gas clouds so they can collapse into new stars. The distribution of gas does not perfectly match the distribution of stars, revealing the galaxy's dynamical history. Stars tend to preserve older patterns, while gas responds more quickly to forces like shocks, gravity, and feedback from young stars. So gas can highlight recent disturbances that stars smooth over. When the two don't align, it suggests that the galaxy's structure has been shaped by ongoing processes rather than remaining static. One well-known feature is a prominent ring-like region of star formation at a radius of roughly 10 kiloparsecs from the center. A ring is an organized band where gas and new stars are concentrated. The scale here is enormous. A kiloparsec is thousands of light years. So this ring sits far out in the disk. Rings like this help astronomers understand how gas flows and how certain orbits or disturbances can gather star-forming material into specific zones. That ring is notable because it is not perfectly centered on the nucleus, indicating an asymmetric disturbance. In a perfectly calm, symmetric galaxy, you might expect a ring to be neatly aligned with the center. When it's offset, it suggests something nudged the system, perhaps an interaction or some gravitational imbalance. This off-center detail provides a valuable clue because small asymmetries can reveal big events in a galaxy's past. Star formation in Andromeda is not uniform. It is patchy and often concentrated in the ring and spiral segments. This means the galaxy is not turning gas into new stars at the same rate everywhere. Instead, certain regions become more active where gas is denser, and conditions allow clouds to collapse. The patchiness you see in certain wavelengths is a map of where the newest stars are being added to the galaxy today. A commonly cited order of magnitude for Andromeda's present-day star formation is around 1 solar mass per year. This is a way of expressing how quickly the galaxy is making new stars in total, not how massive individual stars are. 1 solar mass per year means that, across the whole galaxy, the amount of gas turning into stars each year adds up to roughly the mass of our Sun. It's a steady pace, not an explosive one, and it helps place Andromeda among galaxies that are forming stars more quietly. The galaxy's overall star formation rate is often estimated to be lower than the Milky Way's. Even among large spiral galaxies, star formation activity can differ, depending on how much cold gas is available and how it's distributed. A lower rate suggests that Andromeda is in a calmer phase of building new stars. Comparing it with the Milky Way helps astronomers understand how two similar neighbors can still evolve along different paths. Being in the Green Valley suggests star formation is slowing as the cold gas supply declines. The Green Valley idea is a broad category used to describe galaxies that are not forming stars as intensely as bright blue galaxies, but are not fully quiet, like red, passive galaxies. A slowing pace can happen as gas is used up, heated or removed, and as fewer fresh supplies arrive. It's a gentle stage of change that can unfold over long times. Andromeda's light is spread over a wide area, so its surface brightness is lower than its integrated brightness suggests. Integrated brightness is the total light added up across the whole galaxy, while surface brightness asks how bright each patch of sky appears. Because Andromeda's light is spread thinly across a large apparent area, it can look faint, even though it is intrinsically very luminous. This is why dark skies help so much your eyes need contrast to pick out that diffuse glow. Long exposure images show dust lanes in Andromeda's disk that resemble dark streaks. These lanes appear dark because dust blocks and scatters the light behind it, especially in visible wavelengths. In photographs, dust lanes often trace the structure of the disk and the places where gas is gathered. They act like quiet outlines that reveal where the galaxy's interstellar material is concentrated. Dust lanes in the disk can obscure star-forming regions in visible light, making infrared data especially valuable. Young stars often form inside dusty clouds, and visible light can be absorbed before it escapes. Infrared light passes through dust more easily, and warm dust itself glows in infrared, so infrared observations can reveal activity hidden from optical images. This is one way astronomers get a more complete picture of where star formation is actually happening. Andromeda contains interstellar dust that both absorbs and scatters visible light, changing the apparent colors of background stars. Absorption dims the light, while scattering can redirect it and make some wavelengths more affected than others. This can make stars look redder than they really are, a bit like how distant lights can look muted through haze. Correcting for this dust effect is important for accurately measuring stellar populations and galaxy structure. Dust can be mapped by comparing optical images with infrared emission from warmed grains. Where optical light is reduced by dust, infrared often shows a corresponding glow because the dust absorbs energy and re-emits it as heat. By combining these views, astronomers can estimate how much dust is present and where it sits in the disk. This mapping helps separate what is truly dim from what is simply hidden. In the infrared, Andromeda often highlights warm dust heated by young stars, especially in star-forming regions. Warm dust is a sign of energetic nearby sources, typically young stars that emit strongly in ultraviolet and visible light. The dust absorbs that energy and radiates it gently in the infrared. This allows astronomers to trace star formation even when dust blocks the scene in visible light. In ultraviolet, Andromeda's young massive stars and hot evolved populations become more prominent than in visible light. Ultraviolet light emphasizes hotter sources, including very young, massive stars and certain older stars in advanced stages that also burn hot. This shifts the galaxy's appearance, making active regions stand out more clearly. Observing in ultraviolet provides a different kind of map, one that highlights where the most energetic stellar light is coming from. In radio wavelengths, neutral hydrogen gas can be mapped to reveal disk structure and warps. Neutral hydrogen is one of the most abundant components of a galaxy's gas, and it emits a characteristic radio signal that can be detected across large TAF areas. Because gas can extend beyond the visible disk, radio maps can show structure where starlight is faint. These observations help confirm and measure the warp in the outer disk. Molecular gas, traced by SEO emission, indicates where star formation fuel is concentrated. Molecular gas is the colder, denser phase that forms the cores of star-forming clouds. CO is used as a practical tracer because molecular hydrogen is hard to observe directly in typical conditions. By mapping CO, astronomers can identify where the galaxy's most immediate star-forming reservoirs are located. The balance of atomic gas, molecular gas, and stars differs by radius, reflecting the galaxy's evolution. Inner regions can be dominated by older stars and different gas conditions, while outer regions can be more gas-rich but less efficient at forming stars. These changes with radius are like a long-term record of how the galaxy has grown and rearranged material. Studying the balance helps connect present structure to past history. Supernova remnants in Andromeda can be identified via emission lines and X-ray emission. A supernova remnant is the expanding, heated debris left behind after a stellar explosion. As it shocks surrounding gas, it can glow in specific spectral lines, and the hottest regions can emit X-rays. Finding these remnants helps astronomers estimate how often massive stars have died and how explosions shape the interstellar medium. X-ray binary systems with a compact object accreting from a companion are abundant enough in Andromeda to study population statistics. These systems include a neutron star or black hole pulling material from a nearby star. As the material spirals in, it heats up and releases strong X-rays. With a large enough sample in one galaxy, astronomers can compare where these systems occur and how they relate to different stellar populations. Because Andromeda is external, astronomers can examine an entire galaxy's X-ray source population in one field of view with sensitive X-ray observatories. In the Milky Way, our view is complicated because we're inside the disk, looking through dust and crowded star fields. With Andromeda, the whole system is laid out in front of us as a single object. That clean perspective makes it easier to compare the bulge and disk and to study how X-ray sources are distributed across the galaxy. Many nova thermonuclear eruptions on white dwarfs have been detected in Andromeda because it is observed repeatedly for monitoring programs. Nova are sudden brightenings caused by runaway nuclear burning on the surface of a white dwarf in a binary system. Because Andromeda is watched often, these brief events are more likely to be caught and recorded. Over time, the accumulated detections become a rich dataset for understanding how common these systems are. The nova rate in Andromeda provides clues about the population of close binary systems. A rate is more than just a count. It's a way to infer how many binaries exist that are capable of producing nova. Since nova depend on mass transfer and specific binary conditions, the frequency of events helps constrain how binary stars evolve. In a large galaxy like Andromeda, this becomes a powerful statistical tool. Some surveys use Andromeda to test automated transient detection because many variable and transient sources appear in repeated imaging. When a field contains many stars and occasional eruptions or brightenings, it becomes an ideal place to test whether software can reliably detect change. Andromeda provides both a challenging environment, crowded with sources, and a scientifically meaningful one. Improvements in automation help astronomers handle the flood of data from modern time domain surveys. The disk's dust can hide some optical transients, making infrared follow-up valuable. If an event occurs behind or within dusty regions, visible light can be dimmed enough to be missed or underestimated. Infrared observations can cut through that dust more effectively, revealing what might otherwise remain hidden. This is one reason multi-wavelength observing is so important when studying change and activity in galaxies. Andromeda's proximity makes it a prime target for supernova searches in nearby galaxies. Supernovae are rare, so astronomers watch many galaxies repeatedly to catch them early. Andromeda is close enough that its events can be studied in detail, and its large size means there is a lot of stellar material where a supernova might occur. Each nearby supernova becomes a chance to learn about stellar death, distance measurement, and the impact of explosions on galaxies. Because Andromeda is large on the sky, wide-field cameras are especially useful for capturing its full extent. A narrow view might only see the bright center and miss the outer disk and surrounding features. Wide-field imaging allows astronomers to study the galaxy as a whole system, including faint outskirts and extended structures. This broader coverage helps connect detailed studies of small regions to the galaxy's overall shape and environment. For a long time, Andromeda was simply bright enough in the sky to be noticed by people who had no telescopes at all, especially in places where the night stayed truly dark. Even though it looks faint compared to stars, it stands out because it isn't a pinpoint. It's a soft, extended glow, and that unusual look made it memorable across generations. The fact that humans could notice another galaxy with the unaided eye is a quiet reminder of how luminous and large Andromeda truly is. Before astronomers understood what galaxies were, Andromeda was often described as a DE nebula, a word once used for many fuzzy objects in the sky. Some nebulae are clouds of gas inside our own galaxy, but Andromeda is something far larger. At the time, observers didn't yet have the evidence to separate clouds in the Milky Way from entire other galaxies. This earlier label captures a moment in science when the universe still seemed smaller than it really is. When astronomers realized Andromeda is an external galaxy, it helped confirm that the universe contains many galaxies beyond the Milky Way. This single shift changed the scale of everything. The Milky Way went from being the universe to being one galaxy among countless others. Andromeda became a clear example that the faint smudges in the sky could be whole stellar systems. That realization opened the door to modern cosmology and the study of how galaxies form and evolve across time. Andromeda's large angular size on the sky means that photographs often capture it together with foreground star fields that actually belong to the Milky Way. In a single image, you can see stars that are relatively nearby, and behind them, the distant glow of another galaxy. This layered view is one reason Andromeda images feel so rich. They show our local neighborhood and a much larger structure beyond it. It's also a practical challenge, because astronomers have to separate Milky Way stars from Andromeda's own stars when they analyze the data. Even modest binoculars can show Andromeda as an oval glow with a brighter central region, which is essentially the galaxy's bulge and inner disk blending together. Binoculars gather more light than your eyes alone, so they make the faint outer parts easier to notice. The brighter center appears because there are many more stars packed into the inner region. This simple binocular view is a gentle preview of the galaxy's true structure, a dense core surrounded by a broader, flatter disk. Small telescopes can reveal a brighter core and clearer hints of an extended disk when the sky is dark enough. The core is bright because starlight is concentrated there, while the disk spreads outward and becomes more diffuse. Under good conditions, the disk doesn't look like a sharp boundary. it fades gradually into the background sky. This gradual fading matches how galaxies really work. They don't end suddenly, but become thinner and fainter as you move outward. A major reason Andromeda looks soft to the eye is that most of its visible light comes from older and intermediate-age stars, not only from newly formed hot stars. Younger stars can be bright, but they are fewer and often confined to specific star-forming regions. Older stars, especially those in the bulge and broad disk, contribute a steadier, more widespread glow. This is part of why Andromeda's overall appearance in visible light feels smooth and calm rather than sharply sparkling. Atmospheric clarity and light pollution strongly affect whether Andromeda is easy to see, because it is a low-contrast object. Bright city lights raise the background brightness of the sky, which can wash out a diffuse glow even if the galaxy's total light is substantial. Moisture or haze in the atmosphere can also scatter light, further reducing contrast. This is why the same galaxy can look obvious from one place and nearly invisible from another. Andromeda's disk shows spiral structure, and astronomers can trace these patterns not only in ordinary images, but also in observations that highlight ND. Star formation. Spiral features often become clearer when you look for the places where young stars and gas are concentrated. In visible light, the arms can be subtle, but in ultraviolet and certain gas emissions, they can stand out more distinctly. Seeing spiral structure in different ways helps astronomers understand how stars, gas, and rotation work together. One of Andromeda's most studied large-scale features is a ring-like region, where star formation is especially active, located roughly 10 kiloparsecs from the center. That distance corresponds to tens of thousands of light-years, so it's a truly vast structure. The ring appears as a broad band where gas has gathered and where new stars are forming more readily than in neighboring regions. Large rings like this are important because they hint at how gas moves and settles inside a galaxy. A ring of star formation is essentially a zone where conditions favor the collapse of gas clouds into new stars, so activity becomes concentrated in a band core. Instead of being evenly spread across the disk, gas can pile up along certain preferred orbits, and when enough collects, gravity can take over locally. The result is a structured pattern of star birth that can persist for a long time. This kind of organized star formation helps explain why galaxies can have recognizable large-scale shapes rather than being random swarms. Ring-like structures in galaxies can form through resonances with a bar or through gravitational disturbances that reshape how gas orbits inside the disk. A resonance is like a repeating gravitational rhythm that can herd gas into certain radii. A disturbance, such as an interaction with another galaxy, can also push material outward or inward and create a ring-like pattern. In practice, astronomers compare ring shapes, gas motions, and nearby companions to decide which explanation fits best. In Andromeda, the ring's off-center placement has been discussed as a clue that something disturbed the galaxy in an uneven way. If the ring were perfectly centered, it would suggest a more symmetric internal cause. But an offset ring can point to a past impact or interaction that nudged the gas distribution. This doesn't mean Andromeda is chaotic today. It means its present structure still remembers a past event through its geometry. The ring contains many star-forming regions that become especially clear in ultraviolet and infrared views, where young stars and heated dust show up strongly. In ultraviolet, hot young stars can brighten these regions, while in infrared, the dust warmed by those stars glows. This combination provides a more complete map of where star formation is happening, including places that visible light might partially hide. It also shows how star formation is both a stellar process and a process involving dust and gas together. The outer disk includes extended faint stellar light, that becomes easier to study with deep imaging surveys designed to detect very low surface brightness features. The outskirts are dim not because there are no stars, but because the stars are spread thinly over a large area. Detecting them requires careful observation and processing to separate real faint galaxy light from background noise. When these regions are mapped, they help reveal how far the disk truly extends and how it transitions into the halo. Many studies describe Andromeda's disk as having both thin disk and thick disk stellar populations. The thin disk is generally flatter and contains many younger and intermediate-age stars, while the thick disk is puffier and often contains older stars with more random motion. A thick disk can form through long-term heating of stellar orbits or through interactions that stir and thicken the disk. This layered structure is a useful clue to how Andromeda has evolved over billions of years. The center of Andromeda hosts a compact nuclear region with complex structure, meaning it is not just a simple bright point. Galaxy centers are crowded environments where gravity is strong and stellar orbits can become intricate. In Andromeda, the nuclear region includes multiple components that influence the observed light distribution. Studying this region helps astronomers understand how stars behave close to a supermassive black hole and how galactic nuclei can organize themselves over time. The two main brightness concentrations in Andromeda's nucleus are often labeled P1 and P2 in scientific discussions. These labels make it easier to talk about the distinct peaks seen in high-resolution images. They represent different concentrations of starlight, not two separate galaxies or two black holes. The naming is simply a clean way to track a complex structure that would otherwise be hard to describe precisely. The fainter peak, commonly called P2, is often associated with the true dynamical center of Andromeda in many interpretations. Dynamical center means the point around which the surrounding stars and material orbit in a way that reflects the deepest part of the gravitational potential. Even if it looks fainter in visible light, it can still mark the central anchor point of motion. This distinction between brightest spot and true center is one reason galaxy centers can be surprising. The brighter peak, P1, is offset and is often explained as a region where stars linger longer near the farthest part of their elongated orbits, making that area appear brighter. When orbits are eccentric, stars move more slowly near their turning points, so more stars are found there at any moment. That creates a natural brightness enhancement without requiring a separate object. This kind of explanation is a calm example of how geometry and motion can shape what we see. An embedded compact cluster of hot stars in the nucleus is sometimes labeled P3, adding another layer to the central region's structure. Hot stars shine strongly in ultraviolet, so this cluster can stand out more in certain wavelengths than in ordinary visible images. The presence of such a cluster suggests that even near the center, stellar populations can be mixed and varied. It also shows that the nuclear region is not only about old stars and gravity, but can include relatively energetic stellar groups as well. The mass of Andromeda's central black hole is commonly given in the tens to hundreds of millions of solar masses, depending on the measurement approach and assumptions. Estimating this mass relies on tracking how fast stars move near the center and how their orbits respond to gravity. Different datasets and models can yield different values, especially when the region is complex. Still, all results point to a black hole far more massive than any star, quietly shaping the central dynamics. Variability from the nuclear source has been observed in X-rays and radio, consistent with low-level accretion activity. Accretion means matter slowly falling inward, heating up, and emitting radiation along the way. In Andromeda, this process appears subdued compared with bright, active galaxies, but it is not perfectly constant. The small changes in brightness provide information about how gas behaves near the black hole when the system is relatively quiet. Stars in Andromeda's bulge are generally older, on average, than the stars in its most active star-forming regions. This is a common pattern in large galaxies. The center often holds older stellar populations, while new stars form more readily in certain parts of the disk. Older stars tend to be redder and less luminous individually than massive young stars, but they are numerous. Their presence makes the bulge glow steadily and strongly. Bulges can preserve evidence of early galaxy assembly because many bulge stars formed long ago, and their properties carry the imprint of those early conditions. The ages, chemical compositions, and motions of bulge stars can reveal whether the bulge grew rapidly in the distant past or more gradually. In Andromeda, the bulge's prominence makes it especially valuable for studying such questions. It serves as a kind of historical archive written in starlight and motion. The bulge's stellar motions differ from the disk's more orderly rotation, reflecting the different roles these components play. In the disk, stars mostly move in a coordinated rotation around the center, like lanes of traffic on a vast circular track. In the bulge, motions are more mixed, with stars following more varied orbits. This contrast helps astronomers identify where the disk ends and the bulge begins, and it also hints at different formation pathways for each region. The disk rotates, and its rotation curve provides evidence for dark matter beyond the luminous components. A rotation curve is a plot of how orbital speed changes with distance from the center. In a system containing only visible matter, you might expect speeds to drop at large radii, but many galaxies show speeds staying high. This suggests there is additional unseen mass-dark matter extending far beyond the bright disk. Measurements of rotation in gas and stars can show slightly different kinematic patterns because gas responds differently than stars to forces in the disk. Gas can be compressed, shocked, and influenced by feedback from star formation, while stars behave more like long-lived test particles in the gravitational BP field. So when astronomers compare gas motions to stellar motions, they can learn about both gravity and the internal weather of the galaxy. Differences between traces can also reveal warps, streaming motions, and past disturbances. Andromeda's disk includes large regions where gas densities are too low for intense star formation, even though stars are still present. Star formation generally requires cold, dense gas clouds that can collapse under gravity. If the gas is too diffuse, clouds don't form efficiently, and the birth rate of new stars stays modest. This helps explain why Andromeda's star formation is concentrated in certain zones, rather than being equally active across the entire disk. Galaxies with modest star formation rates can sit in a transitional green valley between actively star-forming blue galaxies and more passive red galaxies. This is a broad observational category based on a galaxy's overall color, which is influenced by the mix of young blue stars and older redder stars. If a galaxy is forming fewer new massive stars, its light gradually shifts away from bright blue. In that sense, Green Valley describes a gentle middle state where star formation is present but subdued. Andromeda's halo contains stars spread out at extremely low densities compared with the disk, creating a vast, faint envelope around the bright galaxy. Halo stars can be very old, and they often move on orbits that are less orderly than disk orbits. The halo also contains remnants of past mergers, so it is not always smooth and uniform. Even though the halo is faint, it carries a lot of information about how the galaxy grew. Halo stars preserve a kind of fossil record of past accretion, because many halo stars were added when smaller galaxies were pulled in and disrupted. Those stars can retain distinct chemical signatures and coherent motions, long after the original small galaxy has been torn apart. By studying these properties, astronomers can reconstruct parts of Andromeda's assembly history. It's a quiet, patient kind of detective work that turns faint starlight into a story of long-term growth. Stellar streams in Andromeda's halo are elongated structures formed when dwarf galaxies or star clusters are tidally disrupted by Andromeda's gravity. Over time, the debris stretches out along the orbit, producing a thin or broad trail depending on the original object. Streams do not appear instantly, they emerge gradually as the disrupted system disperses. Their existence shows that galaxy growth is not only about smooth evolution, but also about the gentle capture and reshaping of smaller neighbors. Streams can appear as shells, loops, or ripples when the debris wraps around the galaxy over time, creating layered patterns in the halo. This wrapping happens because stars in the debris have slightly different energies and orbital periods, so they spread out and fold over themselves in phase space. The resulting shapes can look like faint arcs or nested structures in deep images. These forms help constrain when an accretion event happened and how the stars moved afterward. The existence of multiple streams implies Andromeda has experienced several accretion events rather than being built in a single clean formation episode. Each stream can represent a different disrupted companion, each with its own path and history. Over billions of years, these events add stars to the halo and can subtly influence the disk. This is part of why large galaxies are often described as having grown hierarchically, by combining with smaller systems over time. Mapping halo substructure helps constrain how galaxies grow through mergers in the standard cosmological framework. In that framework, structure forms from smaller pieces to larger ones, and galaxies build up by accreting companions. The patterns in Andromeda's halo streams, shells, and gradients are real observational tests of those ideas. When models reproduce these kinds of features, confidence grows that we understand the broad outlines of galaxy assembly. Andromeda's globular cluster system is described in many catalogues as richer than the Milky Way's, meaning it contains a large population of these dense, ancient star clusters. Globular clusters are among the oldest stellar systems, and their presence in large numbers provides a powerful set of traces for a galaxy's history. They orbit in the halo and outer regions, where they can survive for billions of years. A rich system suggests a long, active history of cluster formation and possibly accretion of clusters from smaller galaxies. A commonly cited count is on the order of hundreds of globular clusters associated with Andromeda, showing that its halo is populated by many long-lived stellar groupings. Each cluster is a tightly bound collection of stars, often very old, packed into a relatively small volume compared to the galaxy as a whole. The sheer number means astronomers can study trends across a large sample, such as how cluster properties change with distance from the center. This population also acts as a set of beacons that help map the galaxy's gravitational field. Globular clusters are dense, gravitationally bound groups of old stars that orbit in the halo and outer regions, and they can be thought of as stellar cities made well, mostly of ancient inhabitants. Their stars tend to be low in heavy elements compared with younger disk stars, reflecting the chemistry of the early universe. Because they are compact, they stand out as distinct objects even at large distances. Studying them helps astronomers understand early star formation and the conditions under which the first large star clusters formed. Some of Andromeda's globular clusters are exceptionally luminous compared with typical globular clusters in the Milky Way. High luminosity often correlates with high mass, meaning these clusters contain more stars and have deeper gravitational wells. Such clusters can survive more easily against tidal forces and internal processes that dissolve smaller clusters. Their existence raises interesting questions about whether they formed unusually massive from the start or grew through mergers of smaller clusters. Mayol II lies far from Andromeda's nucleus, showing that massive clusters can remain intact even on wide orbits over very long times. A wide orbit places the clustering regions where the tidal forces from the central bulge are weaker than in the inner galaxy. That can help preserve the cluster's structure. At the same time, being far out means it can serve as a useful tracer of the outer halo's gravity and history. Some studies suggest Mayol, the 2nd of May, be the remnant nucleus of an accreted dwarf galaxy, rather than a normal globular cluster, which would make it a bridge between clusters and galaxies. If a dwarf galaxy is stripped of its outer stars by tidal forces, its dense central nucleus could remain as a compact object resembling a massive globular cluster. This idea connects directly to hierarchical growth. The galaxy gains not only stars, but also compact remnants of the systems it absorbed. Whether or not this is the final explanation, it shows how Andromeda's outskirts preserve clues to past interactions. Globular clusters can help trace Andromeda's mass distribution because their velocities respond to the galaxy's overall gravitational potential, including the unseen dark matter halo. By measuring how fast clusters move and how their motions change with distance, astronomers can estimate how mass is spread out. Clusters are especially useful in the outer regions where the bright starlight of the disk fades. In that sense, globular clusters serve as long-lived test particles for mapping gravity. The spatial distribution of globular clusters helps reveal how Andromeda assembled its halo over time, because clusters can be formed in place or brought in through accretion. If some clusters share similar orbits, metallicities, or locations along streams, it can suggest they arrived together from the same disrupted companion. Patterns in where clusters are found more concentrated near the center or spread widely also tell us about the galaxy's past environment. This turns a population of star clusters into a map of long-term galaxy growth. Andromeda has 2 bright companion galaxies, M32 and M110, that are easily included in photographs because they sit close to Andromeda in the sky. They appear as distinct fuzzy objects near the main galaxy, giving a visual sense that Andromeda is not isolated. Companions like these can interact gravitationally with their host over time. Their presence helps illustrate how large galaxies are often surrounded by smaller satellites in a broader system. M32 is a compact elliptical galaxy, close in projection to Andromeda's bright disk. And its compactness makes it an interesting object on its own. It looks dense and small compared with the main galaxy, which suggests either a naturally compact formation or a history of tidal stripping. Being close in projection also means it is often seen against Andromeda's background light. This makes careful measurements challenging, but also makes the relationship between the 2 galaxies a valuable topic for understanding how satellites evolve near a massive host. M110 is a dwarf elliptical companion that appears more diffuse than M32, showing that even satellites of the same host can look quite different. A more diffuse appearance often reflects a lower stellar density and a different evolutionary history. Dwarf elliptical galaxies generally contain older stars and little gas compared to gas-rich dwarfs. Observing Messier 110 alongside Andromeda helps astronomers compare satellite types and infer how environment shapes small galaxies. The Andromeda system is part of the local group, which is a gravitationally bound collection of nearby galaxies. Being bound here means the group's gravity is strong enough to keep its members from simply flying away with cosmic expansion. The local group contains a range of galaxy types, from large spirals to tiny dwarfs. Andromeda sits as one of the dominant masses in this group, shaping the motions of many smaller neighbors. The local group's two dominant members are the Milky Way and Andromeda, and their combined gravity largely defines the group's overall structure. Many smaller galaxies orbit one or the other, or move in ways influenced by both. This pairing is one reason Andromeda is so important. It is not just a nearby galaxy, but a major gravitational anchor in our local cosmic SAR. Environment. Studying this pair helps scientists understand how galaxy groups behave in general. The Triangulum galaxy, M33, is another major local group spiral that matters for modeling how the group evolves over time. Although smaller than Andromeda and the Milky Way, it still has enough mass to influence trajectories and interactions. In long-term orbital models, adding M33 changes what might happen between the two giants. This shows that real galaxy systems are multi-body problems, where several large actors can subtly reshape the future. Interactions between large spiral galaxies can induce warps, trigger ring features, and redistribute gas, even without a direct merger. Gravity can pull on the outer disks, bending them and changing how gas settles into the rotating structure. Gas can be driven into new patterns, sometimes enhancing star formation in certain regions. Over long times, these interactions can gently remodel a galaxy's shape and activity without instantly destroying its disk. Even if the Milky Way and Andromeda eventually merge, direct collisions between individual stars would remain extremely unlikely because stars are air, separated by enormous distances. A galaxy collision is mostly a collision of gravitational fields, not a crash of stars into stars. The stars pass by one another like distant ships in a vast ocean. The dramatic changes come from tides and orbital reshaping, not from physical impacts between suns. The Mamie collision effect of a galaxy encounter would be gravitational, tidal distortions, heating of the disks, and a slow redistribution of stars and gas into new orbits. Tidal forces can stretch out long tails of stars and gas, and repeated passes can stir the orderly disk motion into thicker, more randomized motion. Gas can be funneled inward or flung outward, changing where new stars can form. Over time, the two systems can settle into a new, combined galaxy with a very different structure from either original. Andromeda contains interstellar dust that both absorbs and scatters visible light, which can subtly change how stars behind it appear. When dust absorbs light, it makes objects look dimmer. When it scatters light, it can redirect some wavelengths more than others. This is why stars seen through dusty regions can look redder than they truly are, a little like how distant lights look warmer through haze. Correcting for this effect is essential when astronomers want accurate colors, ages, and compositions of stars across the galaxy. Astronomers can map Andromeda's dust by comparing what they see in optical images to what they detect in infrared emission from dust grains that have been gently warmed. In visible light, dust often shows up as darker lanes because it blocks starlight. In infrared, that same dust can glow because it re-radiates the energy it absorbs as heat. By combining these two views, scientists can estimate both the amount of dust and its distribution, building a clearer picture of where the galaxy hides and where it reveals its starlight. Infrared views of Andromeda often highlight warm dust that is being heated by young stars, especially in regions where star formation is active. Young, hot stars emit a lot of energetic light that dust absorbs, and the dust responds by shining in the infrared. This makes infrared imaging a reliable way to locate star-forming neighborhoods, even when visible light is partially blocked. It also helps astronomers separate older stellar glow from the more recent activity, glow of dust and newborn stars. In ultraviolet images, Andromeda's young massive stars can stand out more strongly than they do in visible light and certain hot evolved stars can also become more noticeable. Ultraviolet light is a marker of higher temperatures, so it naturally emphasizes the hottest sources in the galaxy. This shifts the visual balance, making active, younger regions pop against the broader, older stellar background. Observing in ultraviolet helps astronomers trace where the most energetic stellar populations are located right now. In radio wavelengths, Andromeda's neutral hydrogen gas can be mapped to reveal disk structure and large-scale warps that may be subtle or invisible. Ordinary starlight. Neutral hydrogen emits a characteristic radio signal that can be detected across wide areas, including far beyond the bright optical disk. Because gas often extends farther than the visible stars, radio maps can show the galaxy's true reach and shape. These measurements help astronomers understand how the disk is arranged and how it may have been bent or disturbed over time. Molecular gas in Andromeda is commonly traced by observing carbon monoxide, or CO, which acts as a practical signpost for cold star forming. Material. Molecular hydrogen is the main ingredient in star-forming clouds, but it is difficult to detect directly in many conditions. CO is easier to observe, so astronomers use it as a proxy for where dense, cold gas is concentrated. Mapping SEO helps identify the specific zones where new stars are most likely to form. The balance between atomic gas, molecular gas, and stars changes with distance from Andromeda's center, and this variation reflects how the galaxy has evolved. Inner regions may have different pressures, temperatures, and chemical enrichment than the outskirts, which changes how gas behaves and how efficiently it forms. Stars. Outer regions can be gas-rich, but still form stars slowly if the gas is too diffuse or too stable against collapse. By tracking this balance across the galaxy, astronomers learn how Andromeda has used and reshaped its star-forming fuel over time. Supernova remnants in Andromeda can be identified through characteristic emission lines and through X-ray emission from hot, shocked gas. After a star explodes, its debris expands into surrounding material, heating it and creating glowing structures that can persist for thousands of years. Some remnants are easiest to detect in specific spectral fingerprints that indicate energized atoms and ions. Others stand out in X-rays, where the hottest portions of the shock-heated gas radiate strongly. Andromeda contains many X-ray binaries, systems where a compact object like a neutron star or black hole pulls in material from a companion star. As the material spirals inward, it heats to extreme temperatures and produces bright X-ray light. Because these systems can vary in brightness, they also help astronomers study accretion, how matter behaves when falling into deep gravity wells. The large number of such systems in Andromeda lets researchers compare populations across different galaxy regions. Because Andromeda is an external galaxy, sensitive X-ray observatories can often view its entire X-ray source population in a single coherent picture. This is different from studying the Milky Way, where our inside-the-disk viewpoint makes it harder to build a complete, unbiased map. In Andromeda, the bulge, disk, and surrounding areas are laid out together for comparison. That makes it easier to see how X-ray sources cluster in older regions versus younger star-forming regions. Many nova-brief thermonuclear eruptions on the surface of white dwarfs have been detected in Andromeda because it has been watched repeatedly by monitoring DAPL programs. A nova happens when a white dwarf in a binary system accumulates enough material for runaway nuclear burning on its surface. The event can brighten dramatically and then fade over days to months. Andromeda's steady observation history turns it into a rich place for discovering and studying these recurring cosmic flashes. The nova rate in Andromeda helps astronomers estimate how close binary systems are and how they evolve over time. Nova require a specific setup: a white dwarf, a donor star, and a flow of material between them. So each detected nova is evidence that such a system exists and is active. Over many years, the statistics of nova detections provide a window into the hidden population of compact binaries in an entire neighboring galaxy. Some surveys use Andromeda as a testing ground for automated transient detection because repeated images of the same field contain many changing sources. Automated pipelines must learn to identify real astrophysical changes, while ignoring noise, artifacts, and variations caused by the atmosphere or instruments. Andromeda's crowded background of stars makes this a demanding environment, which is useful for refining detection methods. Better detection tools help astronomers catch rare events quickly and reliably in modern data streams. Andromeda's dense bulge offers an especially rich environment for studying stellar variability because it contains so many stars packed into a relatively small area of sky. When millions of stars overlap in a telescope image, it becomes a challenge to measure changes in individual objects. Yet that same density also increases the chance of finding variable stars and transient events. With careful methods, the bulge becomes a laboratory for understanding how stars brighten, dim, and change over time. Dust in Andromeda's disk can hide some optical transients, which is why infrared follow-up can be so valuable. If a sudden brightening happens behind a dust lane, visible light may be dimmed enough to make the event difficult to detect or interpret. Infrared light passes through dust more easily, offering a clearer view of what's happening. This multi-wavelength approach helps ensure that events aren't missed simply because they occurred in a dusty part of the galaxy. SN 1885A is often discussed as a likely type EAA supernova, based on its location and the properties of its remnant. Type EI events involve the thermonuclear disruption of a white dwarf, and they are especially important because they can serve as distance indicators in cosmology. The fact that this event occurred in Andromeda makes it a historically significant extragalactic supernova. Its classification draws on multiple lines of evidence, including how the remnant appears against the background light near the galaxy's center. Remnants of old supernova in Andromeda can be studied long after the explosion using absorption features seen against the bulge's bright starlight. Even when an explosion is long over, its expanding debris can still leave a subtle signature by absorbing specific wavelengths of light passing through it. This turns the bulge's glow into a kind of backlight, like a lamp behind a thin cloud. It allows astronomers to continue learning about an event that happened more than a century ago. Even though Andromeda is often used for broad, galaxy-scale questions, astronomers can also study how its disk inclination affects observations, because it appears as an elongated ellipse rather than a face-on circle. This tilt changes how dust lanes appear and how easily different layers of the disk can be separated. It also influences how we interpret brightness patterns across the galaxy. Understanding the viewing angle is a key step in turning images into accurate physical maps. Because Andromeda is tilted, astronomers can more easily study vertical disk structure, including thick disk components, than they can in many face-on galaxies. In a face-on view, the disk's thickness is mostly hidden because you're looking straight down onto it. In an inclined view, the disk's layers and the distribution of stars above and below the midplane become more measurable. This helps reveal how the disk has been heated and stirred over billions of years. The near side and far side of Andromeda's disk can be distinguished using the geometry of dust lanes and how they obscure background light. Dust tends to block light behind it, so the placement of dark lanes relative to the bright bulge can indicate which side of the disk is closer to us. This is a subtle observational trick that relies on careful imaging and interpretation. It helps astronomers orient the galaxy in 3 dimensions, rather than treating it as a flat picture. Because the disk is tilted, line-of-sight distances across the disk vary slightly, which can matter when using certain distance indicators or when comparing stellar prabura. Populations across the face of the galaxy. One side of the disk is a bit closer and the other side is a bit farther, even though both are part of the same galaxy. This difference is small compared to the overall distance to Andromeda, but it can still matter for precise work. Accounting for geometry helps reduce systematic errors in measurements. The disk's rotation can be measured using Doppler shifts of gas emission lines across different parts of the galaxy's face. When gas moves toward us, its spectral lines shift slightly to shorter wavelengths. When it moves away, they shift to longer wavelengths. By mapping these shifts across the disk, astronomers build a detailed rotation pattern. This is one of the most direct ways to translate light into motion on a galactic scale. Rotation speeds across Andromeda's disk provide a key method for inferring how the galaxy's mass is distributed. If the speeds remain high far from the center, it suggests there is more mass than the visible stars and gas alone can provide. This is one of the classic signatures leading to the concept of an extended dark matter halo. In Andromeda, as in many spiral galaxies, rotation measurements become a crucial bridge between what we see and what gravity implies. The rotation curve, staying high at large radius, is considered classic evidence for dark matter, because visible matter by itself would typically predict declining dia, speeds in the outskirts. In a simple system dominated by a central concentration of luminous mass, orbital speeds should drop with distance. But spiral galaxies often don't behave that way, which implies a broad distribution of unseen mass. In Andromeda, this behavior helps constrain models of its dark matter halo. Andromeda's baryonic mass includes stars, gas, and dust, but this normal matter does not account for the majority of the gravitational mass inferred from its dynamics. Baryonic refers to the ordinary matter made of protons and neutrons. Astronomers can estimate baryonic mass from starlight and gas observations, but the rotation and motions of tracers indicate there is much more mass overall. This mismatch is one of the clearest, calmest clues that dark matter dominates the galaxy's mass budget. Different methods of estimating Andromeda's total mass using satellite motions, halo star velocities, or rotation curves do not always give exactly the same answer, because each method has different uncertainties and assumptions. Satellites may have complex orbits, halo stars may not be perfectly in equilibrium gas, may show non-circular motions. Each dataset is valuable, but each comes with its own modeling choices. Comparing results across methods helps refine the true range of plausible masses. Mass estimates can be revised as new measurements improve distances, velocities, and the handling of observational biases. Small updates in how far a tracer is, or how fast it moves, can change inferred mass significantly, especially in the outer halo. New surveys also discover additional tracers, like faint satellites or globular clusters, which improves coverage. Over time, mass estimates become more robust as the data grows, and the models incorporate more realistic physics. The halo mass of Andromeda is particularly difficult to pin down because it extends far beyond the bright disk and has limited tracers at very large distances. The farther out you go, the fewer bright objects exist to measure, and the more uncertain the motions can become. Yet this outer region is crucial because it contains much of the dark matter. The challenge is not that the halo is unimportant, but that it is faint and vast, requiring patience and clever methods to map. Satellite galaxies provide tracers at large radius, but using them to infer mass requires assumptions about their orbital anisotropy and whether the system is Cambrien. close to equilibrium. If satellites tend to have more radial or more circular orbits, the inferred mass can shift. If some satellites were recently accreted and not fully settled, that can also affect the interpretation. This is why astronomers treat satellite-based mass estimates carefully, often combining them with other traces. Halo stars provide more continuous coverage than satellites, but they become very hard to measure at extremely low densities, especially far from the Ball galaxy where the star counts are small. Distinguishing Andromeda halo stars from foreground Milky Way stars becomes a major observational challenge. Spectroscopy and careful photometric selection can help, but it takes deep data and large samples. Even so, halo stars are valuable because they can fill in regions where satellites are sparse. Globular clusters provide discrete traces over a wide range of radii, but they can have complex accretion histories that complicate interpretation. Some clusters formed within Andromeda, others may have arrived with swallowed dwarf galaxies. That means their motions might reflect multiple past events rather than a single, smooth distribution. Still, their brightness and longevity make them powerful tools for mapping the gravitational potential, especially when combined with chemical and spatial information. The baryonic fraction in Andromeda's halo is lower than the cosmic average in many discussions, which is consistent with the idea that some normal matter is not in dar. Stars or cold gas, but in diffuse hot gas or has been pushed outward. Galaxies do not keep all their baryons neatly inside visible structures. Energy from supernova and other processes can heat and move gas, making it difficult to detect. This topic connects galaxy evolution to the broader question of where ordinary matter resides in the universe. Andromeda's hot circumgalactic medium may hold a significant portion of its baryons in ionized form, surrounding the galaxy as a large, tenuous atmosphere. This gas is extremely thin, so it does not glow brightly in visible light. Instead, it is often studied through subtle signals like absorption features in the light from background sources. Understanding this hot halo is important because it may be both a reservoir for future gas accretion and a record of past outflows. Absorption line studies using background quasars can probe diffuse gas in Andromeda's extended halo. A quasar acts like a distant flashlight, shining through the halo gas on its way to us. The gas absorbs specific wavelengths, leaving fingerprints in the quasar's spectrum. By analyzing those fingerprints, astronomers infer the presence, composition, and motion of otherwise invisible material around Andromeda. The interplay between Andromeda's halo gas and its satellite galaxies can influence whether satellites keep their gas or lose it, affecting their ability to form new stars. As a satellite moves through hot halo gas, it can experience pressure that strips gas away, a process known as ram pressure stripping. Tidal forces can also remove gas and stars. Over long times, these effects can turn gas-rich dwarfs into gas-poor, quiet systems. Gas accretion from the intergalactic medium is thought to have fueled star formation over cosmic time, though measuring present-day inflow directly challenge you. Galaxies need ongoing supplies of cold gas if they are to keep forming stars for billions of years. Some gas may cool out of the hot halo, some may arrive along large-scale cosmic structures. In Andromeda, this question ties directly to why its star formation is modest today, and how its future evolution might unfold. In Andromeda's disk, the dark dust lanes often trace where gas is gathered, because dust and gas tend to live together in the same broad interstellar clouds. When you see a dust lane cutting across a brighter background, you are often seeing a region where material is denser and more structured. Those denser zones are important because they are the places where gas can cool, clump, and sometimes form new stars. So the dust lanes are not just shadows in a photograph there, a useful map of where the galaxy's raw material is concentrated. Spiral arms in Andromeda can be followed using the signposts of young stars, glowing H2 regions, and molecular gas, even when older. Stars look smoother and more evenly spread out. Young stars and H2 regions trace recent star formation because massive newborn stars energize nearby hydrogen gas, making it shine. Molecular gas highlights where future stars can form, since it represents cold, dense reservoirs. By combining these traces, astronomers can outline spiral structure, even if the older stellar light doesn't show sharp arm contrast. In some wavelengths, Andromeda's star-forming ring becomes more visually dominant than the classic spiral arm pattern, changing the way the galaxy appears. This happens because different wavelengths emphasize different ingredients. Ultraviolet highlights hot young stars, and infrared highlights worn dust, both of Chu, which can strongly trace the ring. In visible light, the broad, older stellar population can soften the contrast between arms and interarm regions. Looking across wavelengths reminds astronomers that structure in a galaxy depends on what physical component you choose to highlight. A warp in a galactic disk can arise when incoming gas arrives at a slightly different angle than the existing disk, or when a past tidal interaction pulls on the outer B, parts of the galaxy. The inner disk is usually more stable because gravity is stronger and material is more tightly bound there. The outer disk is more easily bent because it is more weakly held and more exposed to external influences. In Andromeda, the warp is a gentle clue that the galaxy's outer regions have been shaped by forces beyond simple, isolated rotation. Warps are common among spiral galaxies, which makes Andromeda especially useful as a nearby case study for understanding why warps happen and how long they last. Because Andromeda is close, astronomers can map its gas and stars in much greater detail than for most galaxies. That detail helps researchers test whether a warp is more closely tied to gas behavior, satellite interactions, or the broader environment of a galaxy group. In this way, Andromeda becomes a benchmark for a phenomenon that appears across the spiral galaxy population. The outer disk's extremely low surface brightness makes it sensitive to background subtraction and calibration in deep imaging, because the light from the galaxy becomes comparable to tiny errors in the measurement process. When astronomers push to see faint structure, they must carefully remove light from the night sky, instrument reflections, and other subtle effects. Small mistakes can produce artificial features or hide real ones. So studying Andromeda's faint outskirts is not only about observing longer, it is also about controlling systematic errors with great care. Using star counts instead of integrated light can extend mapping to fainter levels in Andromeda's outskirts, because individual resolved stars can be dull, detected even where the combined glow is too dim to measure reliably. Integrated light methods struggle when the surface brightness is extremely low, but star counting can still pick out sparse populations one star at a time. This approach requires distinguishing Andromeda's stars from foreground Milky Way stars, which is challenging but possible with color and brightness selection. Star counts therefore offer a practical route to tracing the galaxy farther out than many traditional imaging techniques. The shape of Andromeda's halo can be inferred from the distribution and motions of tracers such as halo stars and globular clusters, because their orbits CE respond to the overall gravitational field. If the halo were perfectly spherical, the tracer distribution and kinematics would tend to follow certain symmetric patterns. If the halo is elongated or triaxial, the patterns can shift in measurable ways. This is one reason astronomers collect both positional data and velocity data rather than relying on images alone. Dark matter halo shapes are actively debated, with possibilities ranging from near spherical halos to more complex triaxial shapes, because different tau, Models and datasets can support different geometries. A near-spherical halo is mathematically simpler and can match some observations, but many simulations and some measurements allow for elongated forms. The true shape matters because it affects how satellites orbit, how streams form, and how the disk responds over time. Andromeda's halo is an important test case because it offers more traces and clearer structure than most external galaxies. Halo substructures can complicate inferences of the smooth halo shape because tidal debris is not always in equilibrium, meaning it hasn't fully mixed coat into a uniform background. If a stream or shell is present, it can bias measurements of density or velocity in the region it occupies. This makes it harder to separate the background halo from the recently accreted features. Astronomers often try to model or mask these structures so they can estimate the underlying halo properties more accurately. Stellar streams in Andromeda's halo can be used as test particles to probe the galaxy's gravitational potential, because the stream's shape and motion are controlled by the halo's gravity. In simple terms, the stream is debris moving along an orbit, and the orbit depends on the distribution of mass in the galaxy. If the halo is heavier or shaped differently, the stream's path and curvature can change. By matching models to observed streams, astronomers can constrain the unseen mass distribution that guides them. The width and coherence of a stellar stream depend on the progenitor's mass, its internal velocity dispersion, and the strength of the host galaxy's tidal field. A more massive progenitor, or one with hotter internal motions, tends to produce a broader stream. A strong tidal field can stretch and heat the debris more rapidly, making it less narrow and more diffuse. This means streams carry information not only about Andromeda, but also about the properties of the smaller system that was disrupted. Streams can show distance gradients along their length, which allows astronomers to reconstruct their three-dimensional geometry rather than viewing them as flat. Features on the sky. One part of a stream may be closer, another part farther, depending on the orbit and how the debris wraps around the galaxy. Measuring these distances requires careful work with stellar populations and distance indicators. When successful, it turns a faint stripe of stars into a true spatial structure with depth and curvature. Streams can also show velocity gradients, and those changes in speed along the stream help constrain orbital parameters such as eccentricity, inclination. Spectroscopic measurements can reveal how quickly stars in different parts of the stream are moving toward or away from us. Combined with positional data, this helps determine the stream's orbit through Andromeda's halo. This kind of velocity mapping is a powerful way to connect observed substructure to the underlying gravitational forces shaping it. Some streams likely originate from disrupted dwarf galaxies, while others can come from disrupted globular clusters, and the difference matters because these progenitors have very different sizes and internal structures. Dwarf galaxies typically have multiple stellar populations and can contain their own dark matter, while globular clusters are compact and dominated by stars alone. Their disruption produces different debris patterns and chemical signatures. By identifying the likely origin, astronomers learn what kinds of systems Andromeda has accreted over time. A disrupted dwarf galaxy typically leaves broader, more complex debris than a disrupted globular cluster, because dwarfs are larger and their stars have a wider range of initial motions. The debris can appear as wide streams, shells, or overlapping features as different parts of the dwarf disperse. Clusters, being smaller and tighter, tend to produce narrower and more uniform streams. This contrast helps astronomers interpret the morphology of halo substructures as clues to what was torn apart. The presence of multiple streams suggests Andromeda continues to grow through minor mergers, not only through very ancient events that have fully mixed away. Minor mergers are encounters where a large galaxy accretes much smaller companions. They can add stars to the halo without destroying the disk, and their debris can remain visible for long times. Seeing multiple streams implies a long, ongoing history of gradual assembly rather than a single, neatly finished formation. Some halo substructures appear aligned with satellite orbits, suggesting ongoing tidal stripping where satellites lose stars as they move through Andromeda's gravitational field. As a satellite orbits, the side closer to the host feels stronger gravity than the far side, creating a tidal stretch. Over repeated orbits, this can peel stars away, feeding the halo with new debris. Alignments between debris and satellite paths help link visible substructure to the present-day dynamics of the satellite system. Comparing the Milky Way's streams to Andromeda's streams provides a cross-check on galaxy assembly, because both galaxies are large spirals but have had different histories and environments. In the Milky Way, we see streams from inside, which can make geometry harder to interpret. In Andromeda, we see them from outside, which can make overall shapes easier to map. Together, the two perspectives help astronomers test whether the same physical processes produce similar patterns in both galaxies. Because we observe the Milky Way from within, Andromeda provides an external viewpoint that can be easier to interpret geometrically, especially for larger spin. Scale halo structure. In our own galaxy, we look through the disk and deal with dust and complex line-of-sight overlap. In Andromeda, the halo surrounds the galaxy in a more straightforward projected view. This outside perspective helps astronomers validate models that they later apply back to the Milky Way, where the view is more complicated. Andromeda's globular clusters can host exotic objects like millisecond pulsars and X-ray binaries, similar to globular clusters in the Milky Way. Globular clusters are crowded environments where stars interact more frequently than in the quiet field. These interactions can form and recycle compact objects into unusual systems. Finding such objects in Andromeda's clusters supports the idea that dense stellar environments produce similar outcomes across different galaxies. Dense clusters enhance close stellar encounters, which increases the formation rate of compact binaries, including systems that later shine strongly in X-rays. When stars pass close, gravitational interactions can exchange partners, tighten orbits, or create new binaries. These processes are rare in low-density regions, but become much more common in cluster cores. This is why clusters are often disproportionately rich in certain types of compact systems compared with the general galactic field. Some Andromeda clusters show evidence for multiple stellar populations, implying that their formation histories were more complex than a single, simple burst of star formation. Multiple populations can show up as subtle differences in color magnitude diagrams or in chemical abundance patterns. This suggests that some clusters either formed stars in multiple episodes or managed to retain and recycle material. The presence of such complexity in Andromeda's clusters allows astronomers to test cluster formation theories beyond the Milky Way. The brightest clusters can be observed with amateur telescopes as faint points near Andromeda, even though resolving their individual stars is not feasible visually. Their brightness is enough to register as distinct objects under good conditions. However, their internal structure remains beyond the reach of small instruments because the stars are too tightly packed and too far away. This contrast highlights how a single point of light can represent a massive, ancient stellar system. Cluster metallicities in Andromeda span a broad range, reflecting formation in different environments and at different times, and sometimes reflecting accretion from smaller galaxies. Metallicity acts like a chemical timestamp. Early forming systems tend to be more metal poor, while later forming systems can be enriched by previous generations of stars. A wide range suggests Andromeda's cluster system did not all form under identical conditions. It also supports the idea that some clusters were brought in through mergers rather than forming only within the main galaxy. Some clusters are associated with specific halo streams, indicating they were accreted together as part of the same disrupted system. If a dwarf galaxy is torn apart, it can contribute both field stars and its own clusters to the host halo. Those clusters may remain near the debris trail, preserving the connection long after the original dwarf is gone. This provides a clean way to link cluster populations to particular accretion events in Andromeda's history. Cluster ages help constrain when major star formation episodes occurred in Andromeda's early history, because many clusters form during periods of strong star formation. If a large fraction of clusters formed around the same time, it can indicate a significant early event or a phase of rapid assembly. If cluster ages are widely spread, it suggests extended or repeated cluster formation. Using clusters as time markers complements what astronomers learn from the ages of field stars. The globular cluster system's total mass and spatial distribution provide additional constraints on Andromeda's merger history, because mergers can addiate clusters and rearrange their orbits. A merger can bring in clusters from the companion, increasing the total population. It can also heat the halo and redistribute clusters into different radial distributions. Matching observed cluster distributions to simulation outcomes helps narrow down plausible formation and accretion pathways. Comparing Andromeda's cluster system to the Milky Way's helps explain why similar mass spiral galaxies can end up with different cluster populations, different halo structures. Differences can arise from different merger histories, different early star formation intensities, or different satellite accretion patterns. Because the Milky Way and Andromeda are the two dominant local group spirals, they provide a rare side-by-side comparison. This comparison helps refine broader theories of spiral galaxy evolution. Satellite galaxies of Andromeda span a range of types, including dwarf spheroidals and dwarf irregulars, which gives astronomers a diverse set of small systems to study in one environment. These types differ in gas content, star formation activity, and structure. Having many examples around one host helps reveal how environment and internal processes shape dwarf galaxy evolution. It also provides tests for how small galaxies survive and change under the gravity of a massive spiral. Dwarf spheroidal satellites typically contain old stars and very little gas, meaning they form few, if any, new stars today. Their lack of gas can come from internal feedback, environmental stripping, or early consumption of their gas supply. Because they're dominated by older populations, they are useful for studying early star formation in small systems. Around Andromeda, these dwarfs help map the range of quiet, gas-poor satellite evolution. Dwarf irregular satellites tend to be more gas-rich and can show ongoing star formation, which makes them look and behave differently from dwarf spheroidals. Gas-rich dwarfs can still form new stars, often in bursts, depending on how their gas is compressed and cooled. Their irregular appearance reflects weaker gravitational ordering and stronger sensitivity to feedback and interactions. In the Andromeda system, they illustrate that not all satellites are quenched in the same way or at the same time. The number and distribution of Andromeda's satellites provide key tests of cosmological predictions about substructure, because modern models predict many small dark matter clumps around large halos. Observations help determine how many of those clumps host visible stars and how they are arranged in space. Discrepancies can reveal either observational incompleteness or the need to refine physical modeling of star formation and feedback in small halos. Andromeda is especially valuable here because its satellite system can be surveyed from an external viewpoint. Some Andromeda satellites show evidence of tidal disturbance from the host galaxy's gravity, such as stretched shapes or signs of stripped material. When a satellite passes close to the host, tidal forces can pull stars away and reshape the satellite's structure. Over time, repeated encounters can reduce the satellite's mass and leave debris in the halo. Observing these disturbances helps confirm that satellite systems are dynamic and that halo growth can still be ongoing. Satellite galaxies can be used as tracers of Andromeda's dark matter halo mass through their orbital motions, because their speeds depend on the depth and extent of Tanti, the halo's gravitational whirl. If satellites move faster on average, it can suggest a more massive halo. If slower, less massive, though interpretation depends on orbital shapes. Measuring satellite velocities requires spectroscopy and careful membership determination. With enough satellites, astronomers can estimate the halo mass out to very large radii, where direct disk rotation measurements no longer apply. Some analyses propose that a subset of Andromeda's satellites lie in a relatively thin plane, which has prompted debate about whether this is a long-lived physical structure or partly an observational and statistical effect. A thin plane would be unusual if satellites were expected to be distributed more randomly. If real and stable, it could imply satellites were accreted along a preferred direction, such as a filament of cosmic structure. Because the implications are significant, this topic remains actively discussed and refined as new data becomes available. Past close passages between Andromeda and the triangulum galaxy M33 have been proposed in some studies and are tested using proper motion Bayesian measurements and modeling. A close passage could help explain certain disturbances, warps, or tidal features in one or both galaxies. But the plausibility depends on the exact three-dimensional motions, which are difficult to measure precisely at these distances. Testing such scenarios shows how astronomers combine kinematics and structural evidence to reconstruct past interactions. The gravitational influence of smaller local group members can alter the long-term orbit of Andromeda relative to the Milky Way, because galaxy motions are influenced by more than just a two-body interaction. Even a third large mass can change the trajectory over billions of years, especially when small differences accumulate. This is why modern models often include multiple interacting galaxies rather than treating the system as isolated. The result is a more realistic, but also more uncertain, picture of long-term evolution. Modern models increasingly incorporate multiple bodies such as the Milky Way, Andromeda, M33, and the Large Magellanic Cloud rather than TRA. Only two, because each adds gravitational influence that can shift future outcomes. In multi-body systems, gravity creates coupled motion, and even modest changes in one body's trajectory can ripple through the rest. Including more bodies makes the modeling better match the real local group. It also explains why predictions about future encounters are now often expressed as probabilities rather than single definitive timelines. The Large Magellanic Cloud can significantly perturb the Milky Way's motion, which in turn affects estimates of the Milky Way-Andromeda collision probability. Because the Milky Way is not a fixed point, its center of mass motion changes when a massive companion like the LMC moves around it. That shift changes the inferred relative motion between the Milky Way and Andromeda. This is a clear example of how local gravitational relationships can influence even the grandest long-term predictions. Central supermassive black holes in a merger scenario would likely sink toward the new center through dynamical friction, a process where their gravity interacts with surrounding stars and gradually drains orbital energy. As they spiral inward, they can form a bound pair. This is not a fast process on human timescales. It is a slow gravitational settling across enormous distances. The result is that the final stages of a galaxy merger are shaped not only by star motion and gas flow, but also by the deep gravity of the central black holes. The timescales for black hole pairing and eventual merger can be very long, depending on how effectively stars and gas can carry away orbital energy, angular momentum. In some environments, gas can help the black holes lose energy more efficiently, tightening the orbit faster. In gas-poor conditions, interactions with stars may dominate, and the process can slow if there are fewer stars in the right orbits to keep extracting energy. This is why black hole mergers are studied as a complex dynamical problem, not a simple, inevitable endpoint. Andromeda's stellar populations span a wide range of ages, from ancient halo stars to younger disk clusters, which allows astronomers to study many bulba, epochs of star formation within one nearby galaxy. Old stars reveal conditions from early cosmic times, while younger stars reveal what the galaxy is doing more recently. By comparing where different ages of found bulge, disk, haloscientists can infer how the galaxy built its components over time. This makes Andromeda a natural laboratory for galactic archaeology, where stars act as historical records. Metallicity in Andromeda varies across the galaxy and is often described as decreasing with height above the disk and with radius, meaning outer and higher regions tend to have fewer heavy elements on average. Heavy elements are produced in stars and spread by stellar winds and supernova, so regions with more long-term star formation become more enriched. Regions that formed earlier or experienced fewer enrichment cycles tend to be more metal-poor. Measuring these gradients helps connect present chemistry to a long history of star birth and stellar death. Metallicity gradients are important because they encode where and how stars formed over the galaxy's history, like a chemical map of past activity. A steep gradient can imply that inner regions formed stars more intensely or for longer periods than outer regions. A flatter gradient might suggest stronger mixing, migration, or merger-driven redistribution. In Andromeda, these gradients provide clues about how the disk assembled and how material moved through the galaxy over time. The bulge can contain metal-rich stars formed in early, intense star formation episodes because central regions often form stars rapidly when gas T densities are high. Rapid early star formation produces many supernova that enrich the surrounding gas with heavy elements, which then become incorporated into later pre-T generations of stars. Over time, this can leave the bulge with a relatively metal-rich population compared to the halo. Studying these bulge stars helps researchers understand what the central environment was like when the galaxy was young. The halo often contains more metal-poor populations, along with debris from accreted dwarf galaxies that carry distinct chemical signatures. Dwarf galaxies can have different enrichment histories, often slower and less efficient than large spirals. When they are accreted, their stars bring in chemical patterns that can stand out from the host's native populations. This makes halo chemistry a powerful tool for identifying which stars likely formed in Andromeda and which may have been imported from smaller companions. Comparing Andromeda's stellar chemistry to the Milky Way's helps test whether two large spirals built themselves in similar ways or followed meaningfully different paths. If both galaxies show similar gradients and chemical patterns, it suggests shared formation processes. If they differ, it can point to differences in merger history, star formation efficiency, or gas accretion. Because the Milky Way and Andromeda are neighbors of similar scale, differences between them carry especially strong interpretive weight. Some halo substructures in Andromeda show relatively metal-rich stars, implying that the disrupted progenitor was fairly massive, because more massive systems tend to enrich their stars more effectively. A small, low-mass dwarf galaxy often remains metal-poor because it forms fewer stars and loses more enriched gas. A more massive progenitor can retain gas longer, form more stars, and build up heavier elements. So metal-rich debris in the halo can be a chemical clue pointing to a substantial accretion event. Andromeda's disk contains both older, redder stars and younger, bluer stars, with the younger populations more concentrated in star-forming regions. Older stars tend to spread out and contribute to the disk's broad glow, while young stars cluster near where they were born. The color difference reflects temperature and mass. Hot, massive young stars appear bluer, while cooler, older populations look redder on average. This mixture across the disk helps astronomers track where star formation has happened recently, versus where the disk has simply accumulated stars over time. Star clusters in Andromeda can be dated from their color magnitude diagrams when the stars are resolved, because the pattern of star brightness and color reveals their evolutionary stages. In a cluster, stars form roughly together, so the diagram shows a clear turn-off point where the most massive stars have already evolved away from the main sequence. By matching this pattern to stellar evolution models, astronomers estimate cluster age. This method turns careful measurement of starlight into a reliable clock for reconstructing the galaxy's timeline. Cepheid variable stars in Andromeda have been used as an essential tool for measuring distances beyond the Milky Way. Cepheids brighten and dim in a regular rhythm, and the length of that rhythm is tightly linked to how luminous they truly are. By comparing how bright a cepheid looks from Earth to how bright it really is, astronomers can estimate how far away it must be. In a nearby galaxy like Andromeda, Cepheids help anchor the distance ladder that supports much larger measurements across the universe. RR Lyrae stars in Andromeda trace very old stellar populations and help map the ancient halo. These stars also pulsate in a predictable way, but they belong to older, lower mass populations than Cepheids. Because RR Lyrae are common in old halos and globular clusters, finding them tells astronomers where very early generations of stars are concentrated. Their presence is like a quiet signal that a region has been stable and old for a long time. By charting where RR Lyrae appear, scientists can sketch the shape and extent of Andromeda's oldest stellar structures. The tip of the red giant branch method can be applied to resolved halo stars in Andromeda to estimate distance. In a population of old stars, red giants reach a fairly consistent maximum brightness before they change their internal structure in a well-understood way. That consistent tip acts like a standard brightness marker. By identifying the tip in Andromeda's halo, astronomers obtain a distance estimate that does not rely on Cepheids. Using multiple independent distance methods helps cross-check results and reduces the chance that any single assumption dominates the answer. Red clump stars provide another distance indicator that can be used in nearby galaxies like Andromeda. Red clump stars are helium-burning stars that cluster in a particular region of a color brightness diagram. Under many conditions, their typical brightness can be calibrated and used as a distance clue. Because they are numerous, they can be especially useful in mapping broader areas where rarer variables might be sparse. In Andromeda, red clump measurements add yet another rung to the set of techniques that keep distance measurements steady and consistent. Because Andromeda is an external galaxy, line-of-sight overlap of different components can complicate measurements of distances and stellar populations. From our viewpoint, the bulge, disk, and halo can overlap in the same direction on the sky, even though they occupy different three-dimensional locations. That means stars at different depths can be mixed together in a single image. Separating them often requires careful selection by color, brightness, or motion. This overlap is one reason Andromeda is both beautifully accessible and scientifically challenging. Dust within Andromeda can bias star counts and color-based analyses if it is not corrected. Dust can dim stars and make them appear redder, which can trick measurements that rely on brightness and color to infer age or composition. In crowded regions, dust can also hide some stars entirely from optical surveys. Astronomers therefore spend a lot of effort modeling extinction and using infrared data to see through obscured areas. Correcting for dust helps turn the observed distribution into a more accurate physical map of the galaxy. Astronomers often combine multiband photometry to separate the effects of dust from the intrinsic colors of stars. By measuring the same stars in several filters spanning different wavelengths, they can see how strongly dust is affecting the light. Dust tends to alter blue light more than red or infrared, producing a recognizable pattern. With enough bands, models can estimate both the dust amount and the star's true properties. This approach is one of the quiet workhorses of modern galaxy mapping. Deep photometric surveys can map star density profiles far into Andromeda's outskirts, beyond where the galaxy's glow is easy to see. Instead of relying on the faint integrated light, these surveys detect individual stars and use their distribution to measure how density falls with distance. That makes it possible to trace the gradual transition from disk-dominated regions into halo-dominated regions. The results help reveal whether the outskirts are smooth or filled with substructure. Deep surveys turn Andromeda's faint edges into measurable territory. Those star density profiles can reveal where the disk light fades and the halo becomes dominant. In the inner regions, the disk's rotation and stellar density define the galaxy's main structure. Farther out, the disk thins, and the halo's diffuse population becomes the primary component. Pinpointing where this shift occurs matters because it marks a boundary between two different formation histories. It also helps interpret other measurements, like metallicity gradients and kinematic heating, in the correct structural context. The transition region between disk and halo can show signatures of past mergers, such as thick disk heating and flaring. A merger or strong interaction can stir the disk, increasing the random motions of stars and puffing the disk up. Flaring means the disk becomes thicker at larger radii, which can happen when stars are heated or when the gravitational balance changes. These features can persist long after the original event. In Andromeda, the disk-halo interface is therefore a sensitive zone for reading ancient gravitational disturbances. Across Andromeda's disk, older stars generally show higher velocity dispersion than younger stars, which indicates long-term dynamical heating. Velocity dispersion is a measure of how random star motions are compared to smooth rotation. Over time, stars can be heated by gravitational interactions with spiral structure, molecular clouds, or past mergers, making their orbits less orderly. Younger stars begin in colder, more organized motions near their birth clouds. This age-motion relationship is a calm but powerful clue to how a disk changes with time. Andromeda's interstellar medium includes cold molecular clouds, warmer atomic gas, and hot ionized phases. These phases exist because gas can be cooled, heated, compressed, and stirred by many processes, from star formation to supernova explosions. Cold molecular gas is the main birthplace of new stars. Warm atomic gas often fills larger volumes in the disk and can act as a reservoir that later becomes molecular. Hot ionized gas traces energetic feedback and can extend into the halo, linking the disk to the surrounding environment. Hot gas in Andromeda can be observed via soft X-ray emission, which helps trace feedback from supernova and stellar winds. When gas is heated to very high temperatures, it emits X-rays rather than visible light. This hot phase can reveal where energy has been injected into the interstellar medium. It can also show whether gas is flowing out of the disk or lingering in a diffuse halo. X-ray observations therefore add a valuable layer to understanding how galaxies regulate themselves. X-ray studies of Andromeda probe both discrete sources like binaries and remnant sand, diffuse emission from hot gas. Discrete sources appear as point-like objects, individual systems producing concentrated X-ray light. Diffuse emission appears as broader glow, often from hot gas spread across regions. Separating these components requires careful data analysis and high-resolution imaging. Together, they provide a fuller picture of both the objects and the environment that make up Andromeda's high-energy sky. The ratio of X-ray binaries to stellar mass provides a way to compare Andromeda to other galaxies. Because more stars generally mean more chances to form binary systems, a mass-normalized ratio helps standardize comparisons. Differences in the ratio can reflect different star formation histories, different binary evolution pathways, or different cluster populations. In Andromeda, this ratio helps place the galaxy within the broader family of spirals and quiescent systems. It's a measured way to connect a galaxy's present X-ray population to its long-term stellar history. Lomus X-ray binaries are often more common in older stellar populations like bulges and globular clusters. These systems typically involve an evolved companion star feeding a neutron star or black hole over long timescales. Older environments provide the time needed for such systems to form and evolve. Dense clusters also boost their formation by encouraging close encounters that can create tight binaries. In Andromeda, seeing these systems concentrated in old regions aligns with how binary evolution is expected to unfold. High-mass X-ray binaries are linked to recent star formation and tend to be associated with the star-forming parts of the disk. Their companion stars are massive and short-lived, so these systems do not last long on cosmic timescales. If you see them, it usually means massive stars were forming relatively recently nearby. This makes HIMARS X-ray binaries useful markers of youthful stellar neighborhoods. In a galaxy with modest star formation, their relative contribution can be smaller than in a starburst. Andromeda's modest present star formation implies its high-mass X-ray binary population is less dominant than in strongly star-forming galaxies. In a starburst galaxy, many massive stars are formed in a short time, creating plenty of high-mass binaries and bright X-ray sources. In Andromeda, star formation is calmer and more localized, so the population mix tilts more toward older systems. This does not mean high-mass binaries are absent, only that they are not the defining feature of the galaxy's X-ray output. The balance of X-ray source types becomes a quiet indicator of the galaxy's overall activity level. Supernova feedback helps regulate star formation by heating gas and driving turbulence in the interstellar medium. When massive stars explode, they release energy that can stir nearby gas, preventing some clouds from collapsing too quickly. This slows the conversion of gas into stars and can spread heavy elements through the disk. Feedback can also carve cavities and shells, reshaping the structure of the surrounding medium. In Andromeda, feedback is part of the long-term balancing act between making stars and maintaining stable gas conditions. Galactic fountains gas, lifted from the disk, and later falling back can affect chemical mixing and disk evolution. Explosions and winds can push gas upward into the halo, where it can cool and later rain back down. This circulation can redistribute metals and help mix material between different regions of the disk. It also links the visible disk to the broader halo environment. The fountain idea provides a gentle way to picture how galaxies recycle their own material over time. Measuring gas inflow and outflow rates is difficult, but Andromeda's proximity offers more observational constraints than for most distant spirals. Inflows can be faint and hard to separate from regular disk rotation. Outflows can be diffuse and may blend into the hot halo. Yet because Andromeda is nearby, astronomers can use more detailed maps and multiple wavelength tracers to build stronger cases for how gas moves. Even when uncertainties remain, the data quality makes Andromeda a key testing ground for galaxy-scale gas flow ideas. Andromeda provides a useful laboratory for comparing how star formation proceeds in a relatively quiescent spiral versus a starburst galaxy. In a starburst, gas turns into stars rapidly and across large regions. In a quiescent spiral, star formation is steadier and often confined to particular structures like rings or spiral segments. By comparing Andromeda's patterns to more extreme galaxies, astronomers learn what changes when gas density, turbulence, and feedback intensify. This comparison helps clarify which star formation behaviors are universal and which depend on environment. In quiescent spirals like Andromeda, star formation often happens in localized regions rather than in a single galaxy-wide surge. This localization reflects where gas becomes dense enough to collapse and where conditions allow clouds to cool. The result is a patchwork of active zones surrounded by calmer stretches of disk. Over time, those localized regions still build a great many stars. They simply do it in a distributed, steady way. This helps explain why Andromeda can remain luminous and structured without appearing violently active. Gas density thresholds and shear in the disk can limit where giant molecular clouds collapse to form stars. If gas is too thin, gravity cannot overcome internal pressure and turbulence. If shear from differential rotation is strong, it can tear forming clouds apart before they fully collapse. These constraints mean that star formation is not automatic wherever gas exists. In Andromeda, the presence of favored zones, like the star-forming ring, fits naturally with the idea that only certain regions meet the right physical conditions. The ring's concentration of star formation suggests the gas there is dynamically organized, rather than randomly scattered. In other words, the ring is not just a coincidence. It likely reflects how gas flows and orbits within the galaxy. Certain radii can collect gas through gravitational resonances or past disturbances, creating a stable region of higher density. Once the gas is gathered, star formation can proceed more easily. The ring becomes an elegant example of how large-scale dynamics can guide small-scale star birth. Stellar feedback in active regions can create bubbles and shells in the interstellar medium. When young stars emit strong winds and radiation, and when some of them later explode as supernova, they push surrounding gas outward. This can form cavities surrounded by denser shell walls. Those shells can sometimes trigger new star formation by compressing gas at their edges. Even when they do not, they still reshape the disk's gas structure in a way that astronomers can observe. The distribution of dust emission can trace where massive stars have recently heated their surroundings. Dust grains absorb energetic light and re-emit it at infrared wavelengths, so warm dust often marks active or recently active star-forming neighborhoods. This helps astronomers locate regions that might be partially hidden in visible light. It also links the presence of massive stars to measurable changes in the surrounding medium. Dust emission is therefore a quiet but reliable heat map of recent stellar energy. Infrared maps can distinguish between warmer dust near star-forming regions and colder dust spread more diffusely throughout the disk. Warm dust tends to sit closer to young stars and active clouds. Cold dust can be more widespread, mixed with the general interstellar medium, and heated only gently by the broader starlight of older stars. Separating these components helps astronomers understand how energy moves through the galaxy. It also improves estimates of total dust mass and star formation activity. Comparing ultraviolet and infrared emission helps estimate how much star formation is obscured by dust. Ultraviolet light directly traces young, hot stars. but it can be strongly absorbed by dust. Infrared light traces the dust's re-radiated heat, which increases when young stars are present. By combining both signals, astronomers can estimate the seen star formation plus the hidden star formation. This balanced approach produces a more complete picture than either wavelength alone. A lower global star formation rate does not mean a galaxy has stopped forming stars. It means new stars are forming at a slower overall pace. Even a modest rate can sustain ongoing birth in scattered regions across the disk. Over long times, that steady pace still changes the galaxy's population. It also means that the galaxy's appearance can remain relatively stable without explosive bursts. Andromeda's calm star formation is still a living process, just not an extreme one. Over long periods, a slow star formation rate can still add substantial stellar mass to a galaxy. A small amount each year becomes a large amount across billions of years. This is one reason galaxies can keep growing even when they are not in a dramatic starburst phase. The difference is in how quickly the change happens, not whether it happens at all. In Andromeda, the long-term accumulation is part of how its disk has been built and maintained. Because Andromeda is close, astronomers can identify star clusters of different ages and study how clusters dissolve over time. Clusters are not always permanent. Many gradually lose stars as they orbit and experience internal dynamics and tidal effects. By comparing young, compact clusters to older, more dispersed ones, researchers can learn how long clusters typically survive. Andromeda offers a wide range of cluster environments. Bulge, disk, and outer regenster test how conditions affect cluster lifetimes. Young clusters trace recent star formation sites, while older clusters can drift from their birthplaces as they orbit in the disk. A young cluster is often found near gas and dust because it formed from those materials. Over time, the gas disperses and the cluster's orbit carries it onward, sometimes far from where it began. This drift means the present location of an older cluster may not match the location of its original star-forming cloud. Understanding this movement helps astronomers interpret cluster maps correctly. Stellar migration can move stars radially within the disk, smoothing out population gradients over time. A star does not always stay at the same distance from the galactic center where it formed. Interactions with spiral structure and other disk features can exchange angular momentum and shift orbits inward or outward. Over long times, this mixing can blur chemical and age patterns. In Andromeda, migration is one of the processes that can help explain why observed gradients may differ from simple formation models. Disk heating processes increase random stellar motions over time, which can thicken the disk. Heating can come from spiral arms, giant molecular clouds, satellite interactions, and past mergers. As stars gain random motion, they move more above and below the disk plane instead of staying tightly confined. This builds a thicker, puffier component. The thick disk becomes a quiet record of accumulated gravitational stirring. Spiral structure itself can contribute to migration by exchanging angular momentum with stars in the disk. Spiral patterns are not just decorations, they can act like moving gravitational features that nudge stellar orbits. Over time, these nudges can shift stars to new radii without necessarily making their orbits highly chaotic. This subtle reshuffling matters for interpreting where stars of a given age and chemistry are found. In Andromeda, spiral-driven migration is part of how a disk can evolve while still looking orderly. Interactions with satellite galaxies can heat and warp disks, adding another source of long-term change. Even small companions can tug on the outer disk, bending it and stirring stellar orbits. Repeated passages can build up effects gradually, altering the thickness, warp, and substructure. This is one way Andromeda's environment in the local group connects to its internal structure. The disk's present shape can therefore reflect both internal dynamics and external influences. Andromeda is observed across the electromagnetic spectrum, including radio, infrared, optical, ultraviolet, X-ray, and gamma ray. Each band reveals a different component: cold gas in radio, dust in infrared, stars in optical, hot stars in ultraviolet, and energetic and processes in X-rays and gamma rays. No single wavelength tells the full story. By layering them together, astronomers build a more complete picture of how matter and energy are distributed. Andromeda's proximity makes it one of the best targets for this kind of full-spectrum study. Multi-wavelength composites often show distinct physical components: stars in optical, dust in infrared, hot gas and compact objects in X-rays, gas structure in radio. This separation is not just visually pleasing, it is physically informative. It shows where old stars dominate, where new stars are heating dust, and where high-energy events leave hot gas behind. Seeing these layers together helps connect the life cycle of stars to the life cycle of a galaxy. Andromeda's composites are therefore both a map and a synthesis. X-ray maps of Andromeda reveal both diffuse emission and many point sources across the bulge and disk. Diffuse emission often traces hot gas, while point sources often trace compact objects in binaries or remnants. The bulge can appear rich in point sources because it contains many old stars and dense environments. The disk contributes its own pattern, tied to both older populations and pockets of more recent star formation. Interpreting these maps helps astronomers understand how energetic systems are distributed across a galaxy. Bright X-ray sources in Andromeda can include accreting neutron stars and black holes in binary systems. These sources shine because gravity converts infilling matter into heat and radiation. The compact object's strong gravity accelerates the material to high speeds, and friction in the accretion flow produces intense X-rays. Observing these sources helps astronomers study extreme physics in a context tied to a galaxy's overall stellar population. In Andromeda, their distribution also helps test how binaries form and evolve in different environments. The bulge's older stellar population tends to host many low-mass X-ray binaries, which fits expectations that these systems develop over long times. Older populations mean more time for stars to evolve, form compact objects, and settle into mass transfer phases. Dense regions can also increase the chance that encounters create or tighten binaries. The result is a bulge that can be disproportionately rich in certain X-ray sources compared to its share of recent star formation. This provides a direct link between a galaxy's age structure and its high-energy source population. The disk contributes X-ray sources associated with younger populations as well, even if less prominently than in galaxies with very high star formation. Where young, massive stars exist, some will form compact remnants and binary systems that emit X-rays. The disk also hosts older binaries that simply orbit within the disk's structure. So the disk's X-ray population is a mix, reflecting both the disk's long-term history and its present activity. This mixed population is one reason Andromeda's X-ray sky is informative rather than dominated by a single source type. Monitoring programs can catch transient outbursts from X-ray binaries when accretion rates increase, causing a source to brighten dramatically for a time. These outbursts can happen when changes in the accretion disk allow more matter to fall inward quickly. Because the brightening can be temporary, repeated observations are necessary to catch the event. In Andromeda, monitoring builds a time-based understanding of how often such outbursts occur and how they vary between bulge and disk environments. Some X-ray sources in Andromeda are associated with globular clusters, consistent with the idea that dense stellar environments produce compact binaries efficiently. In clusters, close encounters can exchange partners and create tight binaries that are good candidates for mass transfer and X-ray emission. This makes clusters factories for certain exotic systems, compared with the general galactic field. Finding cluster-associated X-ray sources in Andromeda shows that these processes operate beyond the Milky Way as well. It helps confirm that dense stellar dynamics lead to similar outcomes in different galaxies. Hot gas in Andromeda's disk and halo can trace energy injection from past supernova activity. Supernova heat and stir surrounding gas, and some of that energy can remain visible as hot, X-ray emitting plasma. This hot gas can linger in cavities, expand into the halo, or participate in fountain-like circulation. Mapping it helps identify where the galaxy has been energetically active in the past. Even in a relatively calm galaxy, hot gas provides a steady record of stellar feedback. Studying hot gas helps explain how galaxies recycle material and regulate star formation over long times. Hot gas can cool, mix, and eventually return to the disk, feeding future star formation, or it can remain in a diffuse halo as a reservoir. Understanding where it is, how much exists, and how it moves is key to knowing how galaxies maintain themselves. It connects stellar death and feedback to the availability of future star-forming fuel. In Andromeda, the combination of proximity and full galaxy perspective makes this recycling cycle easier to study than in many more distant systems. The Pan-Andromeda Archaeological Survey, often called P and AS, used wide field imaging to map Andromeda's halo and satellite system across a very large area. Wide field mapping matters because halo features can sprawl far beyond the bright disk, and a narrow camera would miss much of the story. P and AS helped reveal Andromeda as a system with extended structure, not just a bright central galaxy. It also provided a consistent dataset that researchers could use to compare many regions under the same observing strategy. Surveys like P and AS revealed faint tidal features that are invisible in shallower data, because low surface brightness structures can be far dimmer than the night. Sky background. These structures are often made of stars spread thinly after a satellite was pulled apart. Seeing them requires deep exposures and careful processing to avoid mistaking artifacts for real features. When those features are confirmed, they become direct evidence of past interactions that still shape the halo today. Wide field mapping is essential for Andromeda because halo substructures can span enormous angles on the sky when projected. Even though the galaxy is far away, it appears large because it is physically huge and relatively close by cosmic standards. Some halo structures can extend far beyond the main disk, occupying areas that require large surveys rather than small, targeted observations. This is why Andromeda is often studied with both wide-field surveys and detailed zoomed-in follow-ups. The depth of a survey determines whether it can detect streams as resolved stars, rather than just faint, integrated light. If a survey is deep enough to pick out individual red giant stars belonging to Andromeda, astronomers can map features more cleanly and measure populations more directly. If it is not deep enough, faint features may blend into background fluctuations and become ambiguous. Survey depth is therefore not just a technical detail, it sets the limit on what kinds of structures can be reliably studied. Color magnitude selection helps isolate Andromeda red giant stars from foreground Milky Way stars, which is necessary because we see Andromeda through a crowded field of nearer stars. The basic idea is that Andromeda's old red giants occupy a characteristic region in color and brightness that can be targeted statistically. This does not remove all contamination, but it greatly improves the signal of Andromeda's halo in the data. With enough stars selected, faint structures become visible as real spatial patterns rather than noise. Foreground contamination is a major challenge because Andromeda lies behind a dense field of Milky Way stars in our line of sight. Many of the stars in an image of Andromeda are not part of Andromeda at all. They are much closer stars in our own galaxy. Separating the two requires careful methods, and the difficulty increases in the faint outskirts where Andromeda's stars are sparse. This is one reason halo mapping relies heavily on statistical techniques and large datasets. Statistical subtraction and proper motion information can reduce foreground contamination in modern analyses. Statistical subtraction compares star counts in regions expected to contain Andromeda stars to nearby control, regions dominated by Milky Way stars, removing the expected foreground pattern. Proper motion helps because Milky Way stars show measurable motion across the sky over time, while Andromeda stars are so distant that their motion is much smaller. Combining these methods makes the remaining Andromeda structures more trustworthy. Spectroscopy of individual red giant stars in Andromeda's halo provides velocities and metallicities, enabling what astronomers call dynamical mapping. Velocities show how stars are moving, while metallicities reveal chemical enrichment history. When both are measured together, researchers can identify coherent groups that likely share an origin, such as a disrupted dwarf galaxy. This turns the halo from a simple cloud of stars into a set of distinct components with different histories. Measuring velocities across streams helps determine whether different visible features come from the same accretion event. Two streams might look similar in images, but if their stars move differently, they are likely unrelated. Conversely, separate-looking structures might share a velocity trend that suggests a single disrupted object wrapping around the galaxy. Velocity data helps prevent mistaken associations based only on appearance. It also refines models of the orbits that produced the debris. Some halo regions show kinematically cold components, meaning groups of stars with unusually low velocity dispersion compared to the surrounding halo. Low dispersion suggests the stars have not fully mixed and still retain the ordered motion of tidal debris. These cold components are often interpreted as relatively recent accretion remnants. Their presence is a sign that Andromeda's halo is still dynamically structured, not entirely smoothed into equilibrium. Some halo substructures show distinct metallicities and stellar ages, allowing astronomers to infer properties of the disrupted progenitors. A more metal-rich stream often points to a progenitor that was more massive or formed stars for longer. A more metal-poor stream can point to a smaller system with less chemical enrichment. Age information adds another layer, indicating when star formation occurred in the progenitor before destruction. Together, these clues help reconstruct what kinds of satellites Andromeda has absorbed. The existence of multiple streams implies that Andromeda has experienced several accretion events, rather than growing only through internal star formation. Each accretion event adds stars to the halo and can leave a recognizable pattern for a long time. Over billions of years, these events build up a complex halo that encodes many episodes of growth. This is one reason Andromeda is considered one of the best places to study hierarchical galaxy assembly from the outside. Because we observe the Milky Way from within, Andromeda provides an external counterpart that is sometimes easier to interpret geometrically. In our own galaxy, dust and perspective make it hard to map the full halo and disk with the same clarity. Andromeda's outside view lets astronomers see the whole structure at once, including how the disk sits inside the halo. This makes Andromeda a reference point for understanding what a large spiral galaxy looks like in full. Andromeda's satellite galaxies span a wide range of types, including dwarf spheroidals and dwarf irregulars, which gives astronomers a natural sample for comparing how small galaxies evolve around a massive host. Some satellites are gas-poor and quiet, while others are gas-rich and still forming stars. These differences show that environment can influence satellites strongly, but not always in the same way. The diversity also helps test theories of how star formation is quenched in small systems. Star formation histories of Andromeda's satellites differ widely, ranging from early quenching systems to those with extended star formation. Some dwarfs seem to have formed most of their stars early and then shut down, while others continued forming stars for much longer. These histories can be reconstructed by analyzing the distribution of stars of different ages. The variety suggests that both internal factors and environmental interactions shape each satellite's timeline. Environmental effects, especially tidal forces and gas removal, can quench star formation in satellites. Tidal forces can pull stars and gas away, reshaping a dwarf and reducing its ability to hold onto star-forming material. Gas removal can also happen as a satellite moves through a host's hot halo, stripping its gas and leaving it unable to form new stars. Over time, these processes can transform a once active dwarf into a quiet, gas-poor system. Andromeda's satellites provide many examples across different distances and conditions. The spatial distribution of satellites can be anisotropic, meaning satellites are not always evenly spread in all directions around the host. This can raise questions about whether satellites arrived along preferred directions, such as cosmic filaments, or whether observational biases influence what is detected. Anisotropy can also reflect the fact that accretion happens along large-scale structure rather than randomly. In the Andromeda system, this topic is closely connected to debates about satellite planes and accretion patterns. Some analyses propose that a subset of Andromeda's satellites lie in a relatively thin plane, which has prompted debate about formation history and DAT. Observational selection. If a plane is real and long-lived, it could imply a shared accretion origin or coordinated orbital behavior. If it is partly due to selection effects or small number statistics, the implication would be more modest. Researchers continue to test this idea with improved satellite catalogues and better motion measurements. The discussion itself shows how Andromeda can challenge simple expectations about satellite distributions. Deep surveys continue to search for faint satellites around Andromeda because extremely low luminosity dwarfs are difficult to detect. The faintest dwarfs contain very few bright stars, and their overall surface brightness can be so low that they blend into background variations. Detecting them often requires wide-area imaging and careful star count analysis. As more faint satellites are found, the known satellite population becomes a stronger test of cosmological models. Dwarf galaxies can host globular clusters, and if such dwarfs are accreted, their clusters can become part of Andromeda's halo population. This creates a natural pathway for building a rich globular cluster system over time. It also means that some of Andromeda's clusters may carry chemical and dynamical signatures of an origin outside the main galaxy. Linking clusters to streams strengthens this accretion picture. In this way, clusters are not only ancient objects, but also historical markers of galaxy growth. M32 is unusually compact and has been studied as an example of a dense elliptical or possibly a stripped remnant. Its small size and high stellar density make it stand out among satellites. One explanation is that it may once have been larger, with outer layers removed by tidal interactions with Andromeda. If stripping played a major role, M32 would be an example of how a massive host can reshape a satellite dramatically. Its present form could therefore encode a long history of gravitational influence. Tidal stripping by Andromeda could explain why some satellites are compact and gas-poor, because repeated close passages can remove loosely bound stars. Gas. As material is stripped, the remaining object can become denser and more centrally concentrated. Gas can be especially vulnerable since it is more easily pulled away or removed by interaction with the host environment. Over time, stripping can change not only a satellite's mass, but also its appearance and star-forming ability. This process helps connect satellite properties to their orbital histories. M110 contains older stars and also shows evidence of intermediate age populations in some studies, suggesting its star formation. History may not have been confined to the earliest times. Intermediate age populations imply star formation continued well after the earliest epoch, at least in some regions. This makes M110 a useful comparison point for understanding why some satellites shut down early, while others continue longer. It also shows that even dwarf elliptical galaxies can have more complex histories than a single simple burst. Some Andromeda satellites have extended stellar halos of their own, indicating internal complexity despite small size. A satellite halo can include older, more diffuse stars surrounding a denser core. This suggests that even small galaxies can experience internal structural differentiation and possibly their own minor accretion events. Studying these halos helps reveal how hierarchical growth operates at smaller scales as well. It also shows that small does not necessarily mean simple. The Andromeda system illustrates hierarchical galaxy growth, a large galaxy surrounded by smaller companions and debris from past accretions. In hierarchical growth, big galaxies become big partly by absorbing smaller systems over time. Andromeda's streams, shells, and satellite population are all consistent with this picture. The galaxy's halo can be read as a record of what it has collected. This framework connects what we see locally to the broader cosmic story of structure formation. Minor mergers can thicken disks, create stellar halos, and deposit streams without destroying the overall disk structure. Because the companion is much smaller, the main disk can survive, though it may be heated and warped. Stars from the smaller system are often spread into the halo as debris, forming recognizable substructures. Over time, repeated minor mergers build up a complex halo, while leaving the galaxy still recognizably spiral. Andromeda's preserved disk alongside its rich halo substructure fits well with this kind of growth. Major mergers can strongly disturb or even destroy disks, but disks can regrow if enough gas remains to settle back into rotation. A major merger involves two galaxies of more comparable mass, which can scramble stellar orbits and produce a more spheroidal remnant. If gas survives the turmoil, it can cool and settle into a new disk, forming stars and rebuilding a spiral-like structure over time. This means morphology can evolve and recover, depending on gas content and orbital geometry. Andromeda's present form suggests that if major events occurred, they did not permanently erase its disk. Some interpretations propose that Andromeda experienced a significant merger a few billion years ago, which could help explain certain halo and disk-ablaire features. A merger of that scale could deposit substantial debris, thicken the disk, and alter star formation patterns. Researchers test this idea by comparing observed substructures, kinematics, and stellar ages to simulation predictions. The scenario remains model-dependent, showing that multiple histories can sometimes match broad observations. Even so, exploring it helps clarify which features require a merger and which can arise from smaller interactions. The timing and mass ratio of any significant past merger in Andromeda are debated and depend on modeling choices and available constraints. Different simulations can reproduce similar present-day features with different initial conditions. Observational uncertainties in distances, velocities, and the interpretation of substructures also affect the conclusions. This is why astronomers use many independent lines of evidence, such as stellar ages, metallicities, and stream geometries. The debate itself reflects how carefully galaxy histories must be reconstructed from incomplete records. Star formation histories inferred from resolved stars contest whether a galaxy-wide enhancement occurred in Andromeda's past. If a major event triggered widespread star formation, it could leave a noticeable population of intermediate-age stars across broad regions. Researchers look for consistent age patterns and for correlations between age and location. Because Andromeda is close enough to resolved stars in many places, it is one of the best galaxies for this kind of direct test. These studies tie large-scale events to the actual ages of stars that formed. A past star formation enhancement would leave signatures such as a cohort of intermediate-age stars with particular kinematics, reflecting how those stars were formed and later stirred. If a merger heated the disk or created a thick disk, stars formed around that time might share characteristic motion patterns. Kinematic measurements help distinguish between stars that formed quietly in a stable disk and those formed during more disruptive periods. Linking age and motion is therefore a powerful way to test scenarios of past interactions. In Andromeda, this approach benefits from the ability to study many stars across multiple regions. Bars, if present, can redistribute angular momentum and move gas inward, influencing central star formation and possibly contributing to ring glare. Formation. A bar is an elongated structure of stars in the central disk that can act like a gravitational conveyor. It can drive gas toward the inner regions, fueling star formation or altering the conditions near the nucleus. Bars can also create resonances that gather gas into rings at certain radii. In Andromeda, researchers weigh bar-driven explanations against interaction-driven explanations when interpreting ring-like features. The relative importance of bars versus interactions in shaping Andromeda's ring and warp remains an active research area because multiple mechanisms can produce similar large-scale patterns. Interactions can offset rings and bend outer disks, while bars can organize gas through resonances and redistribute material. Observations across wavelengths and careful kinematic modeling are used to decide which processes dominate. The possibility of mixed causes is also considered, where internal dynamics and external tugs work together. This reflects how galaxies often evolve through overlapping influences rather than single isolated mechanisms. Andromeda's nucleus is relatively quiet compared to luminous active galaxies, suggesting a low current accretion rate onto its central black hole. A low accretion rate means less gas is falling inward and being heated into bright emission. Many supermassive black holes spend most of their time in such calm states, with only occasional flares or modest variability. Andromeda's proximity allows this quiet activity to be studied in more detail than in many other galaxies. In that sense, it provides insight into what typical black hole feeding can look like. Low luminosity active galactic nuclei can still show flares and variability as the accretion flow changes, even when they are not bright quasars. Small changes in how gas circulates near the black hole can shift the emitted radiation. Observing these variations helps constrain the physics of low-rate accretion, which can be quite different from the intense, luminous accretion in quasars. Andromeda offers a nearby example where variability can be monitored over time. This turns subtle changes into meaningful data about how a quiet nucleus behaves. Because Andromeda is close, astronomers can study nuclear variability with high spatial resolution compared to more distant galaxies. High spatial resolution matters because the nucleus is surrounded by many stars, and separating black hole-related emission from stellar emission is difficult. With sharper imaging, a smaller region can be isolated, reducing confusion. This improves measurements of how the nucleus brightens and fades in different wavelengths. The result is a clearer view of a central black hole in a calm phase. the nuclear region is crowded with stars, complicating the separation of stellar light from emission produced by accretion onto the black hole. In visible and ultraviolet light, stars can dominate what is seen, even when a black hole is present. In X-rays and radio, accretion signatures can become clearer, but interpretation still requires careful modeling. This blending of sources is a practical observational challenge, not a theoretical one. Andromeda's nucleus is a place where technique and astrophysics meet closely. Ultraviolet bright stars in the nuclear cluster can dominate ultraviolet images even when the black hole is faint, showing that stellar populations can outshine accretion in certain bands. These hot stars can be part of compact clusters that stand out strongly at short wavelengths. Their presence means that ultraviolet brightness is not automatically a sign of black hole activity. Instead, astronomers must use multiple bands and careful diagnostics to understand what is producing the light. This complexity is part of what makes galactic centers so interesting to study. The nuclear double structure is a reminder that galaxy centers can host non-axisymmetric stellar configurations rather than simple, symmetric distributions. In Andromeda, the brightness peaks reflect an organized, stable arrangement of stars on eccentric orbits. This kind of structure shows that stellar dynamics near a central black hole can produce surprising patterns that persist. It also illustrates that even in a calm galaxy, the center can be dynamically intricate. The nucleus becomes a small region with a lot of information packed into it. An eccentric stellar disk can persist if it is dynamically stable around the central black hole, meaning the orbits maintain a coherent pattern rather than quickly randomizing. Stability depends on how the stars interact gravitationally and how the black hole's mass dominates the central potential. When stable, the disk can maintain a long-lived asymmetry that creates the observed brightness distribution. This is a quiet example of how orderly motion can create a complex appearance. It shows that complexity does not always require chaos. The orientation and thickness of the nuclear disk influence how the double structure appears in projection from Earth. Because we see the system from a particular angle, geometry affects what looks bright and what looks offset. A thin disk seen at one angle can look very different from a thicker disk seen at another. This is why modeling is necessary. The observed image is a projection of a three-dimensional structure. In Andromeda, understanding that projection helps connect appearance to real orbital architecture. Stellar dynamics near the black hole can be modeled to infer black hole mass from observed velocities, using the way stars respond to gravity in the central region. Faster stellar motions generally indicate a deeper gravitational potential and thus a more massive central object. However, the inferred mass depends on assumptions about orbital shapes and how mass is distributed in stars and dark matter near the center. Modeling tries to incorporate these factors to match observations. Andromeda serves as a key test case because its nucleus is close enough to study in detail. Independent black hole mass estimates can differ because they depend on assumptions about stellar orbits, anisotropy, and mass-to-light ratios in the nuclear region. If stars move more radially or more circularly than assumed, inferred mass can shift. If the stellar population has different mass-to-light properties, that changes how much of the gravity is attributed to stars versus the black hole. Differences between methods are not necessarily contradictions. They can reflect the challenge of modeling a crowded, complex environment. Comparing estimates helps refine both data and theory. A lower global star formation rate in Andromeda does not mean its disk is static. It means the galaxy is evolving through slow internal processes alongside occasional external accretion. Gas still moves, stars still migrate, clusters still dissolve, and the halo continues to mix and absorb debris. Many of the most important changes in galaxies happen quietly over long times, rather than in brief, explosive moments. Andromeda is a nearby example of a massive system that can be active in subtle ways. Its calm pace makes it easier to study long-term mechanisms without the overwhelming brightness of extreme starbursts. Even without a direct Milky Way-Andromeda merger, long-term gravitational interactions can still alter outer halos and satellite orbits over Dani. Billions of years. Gravity acts at great distance, and small tugs accumulated over enormous time can reshape trajectories. Satellites can shift, streams can precess, and halo material can be redistributed even if the two main galaxies never fully merge. This is one reason modern predictions are often probabilistic rather than absolute. The local group is a living system, with motion and change continuing far into the future. Because Andromeda is both nearby and massive, it remains one of the most important galaxies for connecting detailed stellar measurements to galaxy formation. Theory. Few galaxies allow such a combination of whole galaxy perspective and the ability to resolve individual stars in many regions. That combination lets astronomers link the small stellar ages and chemistry to the large halo growth and disk evolution. Over time, the accumulated observations form a kind of long, quiet archive. And as you let that settle in, you can simply remember that in the dark sky, a faint smudge of light can represent an entire neighboring island of stars, still turning, still changing, and still patiently telling its story.